Crete is an island. It has always been an island. That sounds obvious, but it matters more than you might think, because sitting on a beach on Crete in the year 2024, looking out at that deep blue Mediterranean water, you're looking at something that separated Crete from the nearest mainland by at least 40 miles of open sea, even at the times in Earth's history when sea levels were at their lowest. There is no land bridge. There never was one. No shallow crossing, no chain of exposed sandbars you could wade across at low tide. To get to Crete, you need a boat, or at the very minimum, some kind of watercraft. You need the intention to cross, the technology to do it, and the understanding that something worth reaching exists on the other side of that water. Now here's where it gets deeply strange. In 2008, and in subsequent excavations after that, archaeologists working on Crete found stone tools. Not modern stone tools. Not tools left by ancient Greeks or Bronze Age sailors. Stone tools so old, so primitive in their style, that the geological layers they were buried in date them to at least 130,000 years ago. Some researchers think they could be even older than that, pushing towards 700,000 years. Let that number sit for a second. 130,000 years ago at minimum. Modern humans, people like you and me, our species, Homo sapiens, only left Africa and spread into Europe and Asia somewhere around 60,000 to 70,000 years ago. The earliest confirmed modern human presence in Europe doesn't comfortably predate that window by much at all. So if modern humans didn't reach Crete until well after these tools were made, then whoever made them was not us. And whoever they were, they crossed open ocean to get there. That is the mystery sitting at the centre of this entire story. Not just who made the tools, but how and why, and what it means for everything we thought we understood about the cognitive and technological capabilities of the humans or human relatives who came before us. See, for a long time the assumption in paleoanthropology was relatively clean and comfortable. Early hominins, species like Homo erectus or the Neanderthals, were generally considered land-bound. They followed coastlines, they crossed rivers, they moved with the slow drift of populations across connected land masses. But open water crossings, intentional seafaring, that was supposed to be our trick. A modern human trick. A sign of advanced planning, symbolic thinking, complex social organisation. The kind of cognitive firepower that only fully modern brains could generate. The Crete tools don't just complicate that picture. They potentially shatter it. Now I want to be clear about something before we go any further, because this is the kind of topic where it's very easy to race past the evidence toward the most dramatic conclusion. The truth, as it almost always is in archaeology, is messier and more interesting than a clean headline. The stone tools from Crete are real. The dating is taken seriously by credible researchers. But there are genuine scientific debates about exactly how old they are, exactly what species made them, and exactly what their presence on the island actually tells us about intentionality versus accident. We're going to walk through all of that. The evidence, the competing interpretations, the things scientists agree on, and the things they genuinely argue about. Because the honest version of this story is more compelling than any oversimplified version could ever be. What we're really asking is this. Was there a chapter of human prehistory, written not in DNA labs or fossil beds but in flaked stone on a Mediterranean island, that tells us something revolutionary about who was capable of what and when? And is it possible that the story of exploration and seafaring and intentional crossing of open water begins not with us, but with someone who came long before us, someone we haven't yet fully understood? Those are the questions, and over the next however long you've set aside for this, we're going to dig into them properly. Before we do, real quick, if you're listening on Spotify, go ahead and follow the show there. It's completely ad-free, no background music, just the story. Link is in the description, and it's genuinely the best way to support what I do here. So thank you if you do that. And I want to know where you are right now. Drop it in the comments. The city, the time, whether you're driving or lying in the dark at 2 in the morning waiting for your brain to finally stop running. I read those comments, and it's one of my favourite things about making these because it's always Berlin at breakfast, and Vancouver at midnight, and someone in Melbourne on their lunch break, all hearing the same thing at completely different moments in their day. Okay, back to Crete. Back to 130,000 years ago. Back to whoever stood on that shoreline, looked out at water they had no guarantee ended anywhere worth going, and crossed it anyway. Let's figure out who they were. To understand why the Crete discovery is so disorienting, you need to understand what islands actually are in the context of prehistoric movement. Not islands as we think of them today, as vacation destinations or political territories, but islands as evolutionary and archaeological phenomena, because islands don't behave like the rest of the landscape. They operate by different rules, and those rules are exactly what makes finding 130,000-year-old tools on Crete so difficult to explain away. Start with the basic geography. Crete sits in the eastern Mediterranean, roughly 40 miles south of the Greek mainland at its closest point, and separated from the coast of North Africa by about 200 miles of open water to the south. It's a substantial island, around 160 miles long, mountainous with real ecological diversity. Not a tiny exposed rock, but an actual landmass with rivers and forests and coastline. Worth living on if you could get there. The problem is getting there. Here's the thing that trips people up when they first hear about Pleistocene sea levels. During ice ages, massive amounts of water get locked up in glaciers and ice sheets, and global sea levels drop. During the last glacial maximum, roughly 20,000 years ago, sea levels were something like 400 feet lower than they are today. That sounds like it should turn the Mediterranean into a very different place, exposing vast stretches of seafloor and potentially connecting islands to the mainland. And in some parts of the world, lower sea levels really did create land bridges. The Bering Land Bridge between Asia and North America. The exposed shelf between Australia and New Guinea. These connections allowed animals and people to walk between land masses that are now separated by ocean. But here's what the geology of the eastern Mediterranean tells us, clearly and unambiguously. Crete never connected to the mainland, not during the last glacial maximum, not during older glacial periods, not at any point in the time frame we're discussing. The seafloor between Crete and the Greek mainland drops into water that is deep enough that even the most dramatic sea level drops during the Pleistocene would not have exposed a continuous land surface. The channels simply go too deep. You'd need sea levels to fall by something like 800 to 1,000 feet to even begin to think about partial connections, and that's not what the paleoclimate record shows. What you get with lower sea levels is a somewhat different coastline, exposed continental shelves, different beach positions, islands that were larger than they are today. What you don't get is a walkable path to Crete. This is the critical distinction between what geologists call a stepping stone crossing and a land bridge crossing. A land bridge is exactly what it sounds like, dry land connecting two places. You can walk across it, animals cross it, plants colonize it. It's just geography, but a stepping stone crossing involves open water between each step. Even if the steps are close together, even if they've been shortened by lower sea levels, water still has to be crossed intentionally. And the difference between those two scenarios in terms of what it implies about the travellers is enormous. Think of it this way. The fact that Flores in Indonesia was reached by hominins over 700,000 years ago was controversial, precisely because the channels around Flores never fully closed even during glacial maxima. Whatever got to Flores crossed water to do it. Crete is the same situation, but with an even deeper channel and an even more compelling mystery attached to it. Islands function as what biologists sometimes call ecological filters, because reaching an island requires either the ability to cross water or extraordinary luck in the form of rafting on debris. The populations that end up on islands are not random samples of mainland life. They're filtered. Most mainland species never make it. The ones that do tend to be good swimmers, capable of flight, or small enough to survive on drifting vegetation. Large land animals with no particular affinity for water almost never colonize islands through natural means. This is why island faunas often look so strange compared to nearby mainlands, because the normal rules of who gets where have been replaced by a much harsher selection process. The filter only lets through a specific kind of traveller. For hominins, for any human relative, that filter is even more stringent. You can't drift to Crete on a log the way a small lizard might. You're too big, too heavy, too metabolically demanding, and the crossing is too long. By the time any piece of floating debris carrying a large primate drifted from the Greek mainland to Crete, the primate would be dead from dehydration. The distances and the currents in the eastern Mediterranean simply don't allow for accidental arrival of anything large. We'll get into that debate more later, but the geographic baseline matters. Crete is not the kind of place you end up by accident if you're a large mammal. So when archaeologists find tools on Crete, what they're really finding is evidence that the filter was crossed. Something got through that geographically shouldn't have been able to get through without intention. And the question shifts from whether the crossing happened. The tools make that undeniable to how it happened and what cognitive and technological capacity that implies. Now, to even begin answering that question, you need to know what the coastline actually looked like at the time the tools were deposited. And this is where a different kind of science enters the story. Reconstructing ancient coastlines is not straightforward. You can't just subtract 130 feet from current sea levels and assume you know where the beaches were. You also have to account for something called isostatic adjustment, the way the Earth's crust itself moves in response to the weight of ice sheets. During glacial periods, the enormous weight of ice sheets pushes the crust down in some places and causes rebound in others. When the ice melts, the land continues adjusting, sometimes for thousands of years. So the relative position of land and sea at any given location depends not just on global sea levels, but on local crustal movement, which varies by region. For the eastern Mediterranean, geologists have done substantial work reconstructing what conditions looked like during the Pleistocene at various points in time. They use a combination of underwater topographic surveys, sediment core analysis from the sea floor, isotopic records from cave formations, and modelling based on known ice volume estimates. What emerges is a detailed picture of how the coastline shifted over time, where beaches were exposed and then submerged again, which channels narrowed and which remained deep. For the period around 130,000 years ago, which falls during the early stages of the last interglacial period, sea levels were actually close to or slightly above modern levels. The preceding glacial period had ended and the ice was melting. What this means is that the sea crossing to Crete around that time was not shorter than it is today. It was roughly the same distance, or possibly even a bit more water than we're looking at now. Whatever crossing was made, it was made across an open sea that looked recognisably similar to the Mediterranean we know. Archaeologists working on this problem use all of this geological data to set the parameters of their investigation. Before you can ask who crossed to Crete, you have to establish precisely how much water there was to cross, where the nearest possible departure points were, and what the currents and winds in the region were doing at the time. It's detective work that moves between disciplines, from sediment cores to oceanographic modelling to stone tool typology, each line of evidence constraining what the others can claim. What the geological picture confirms, unambiguously, is that Crete has been an island throughout all of human prehistory. It was an island before our species existed. It was an island when Homo erectus was walking across Asia. It was an island when Neanderthals were hunting in European forests. And it was an island when something left those tools in the red sediments of Crete's southern coast. There is no version of the geology that makes this easy. No version where you can say, well, the sea level was lower, so maybe they just walked most of the way. The sea was there. It has always been there. And that means the tools represent something that, by conventional thinking, should not have been possible for whatever species was present in the Mediterranean region 130,000 years or more ago. That's the foundation. That's why geographers and geologists take this discovery seriously enough to sit with it, because the physical setting doesn't allow for convenient explanations. The island was an island. The crossing was a crossing. And whoever made it either had the capability to do so intentionally, or something happened that we don't yet have a good framework to explain. What the tools themselves look like, and what they tell us about the hands and minds that made them, is where the story gets more complicated still. Because the tools are not what you'd expect if you were imagining a sophisticated seafaring culture. They're old, they're simple. And that simplicity is one of the strangest and most fascinating parts of this entire puzzle. When news stories talk about 130,000-year-old tools on Crete, they make it sound like somebody dug up a neat little campsite with a hearth, some bones, and a pile of stone tools sitting right where they were left. That's not what happened. The real story begins with a very different kind of archaeology. Not a single dramatic excavation, but years of walking, systematic walking, archaeological survey. Southern Crete is cut by a series of deep gorges that run from the mountains down to the Libyan Sea. Rivers and seasonal streams have carved their way through layers of limestone and sediment, exposing old terraces, ancient riverbanks and shorelines that were laid down hundreds of thousands of years ago, and then stranded as the landscape rose and the rivers cut deeper. It's along these terraces, especially near the southern coast around places like Placius, Prevali and adjacent valleys, that the controversial tools turned up. If you were there with the survey teams, what you'd see is not a dig, but people spaced out in lines, slowly crossing eroded slopes and terrace surfaces, eyes trained on the ground. No trowels, no brushes, just boots, clipboards and the patience to stare at rocks for hours. Most of what they're walking across is just that, rocks. Limestone fragments, river cobbles, pebbly gravels, bits of weathered chert. It all blends together, but every so often something stands out. An edge that looks too straight, a flake scar at just the right angle, a piece of stone that doesn't match anything else nearby. Over time, these somethings began to cluster in specific places on those old surfaces. Not single odd stones, but little concentrations of material, cores, flakes, a few larger, more shaped pieces that look strikingly like crude hand axes or bifaces. If you're not familiar with stone tools, core and flake sounds underwhelming, but in Paleolithic archaeology, that's the bread and butter of what human activity looks like. A core is the chunk of stone that someone has deliberately struck to knock off flakes. It's the parent block, the thing you hold and hit with a hammerstone. A flake is the piece that comes off, thin, sharp, often used directly as a cutting or scraping tool. In many early technologies, the flakes are actually the main goal. The core is just the scaffold you remove them from. On these Cretan terraces, survey teams found both. Cores with multiple removal scars radiating from a prepared surface. Flakes with the characteristic features of deliberate napping. A striking platform where the blow landed. A bulb of percussion. Rippling fracture lines radiating from the impact point. Sometimes you see negative flake scars on a core arranged in a pattern that only makes sense if someone understood where to hit to get a usable piece. Mixed in with these are a small number of larger tools, thick, bifacially worked pieces that look, in plan view, like worn-down hand axes or heavy-duty cutting implements. They're not elegant in the way classic Acheulean hand axes from Africa or Europe can be, but the basic idea is the same. Take a suitable stone, thin it by removing flakes from both faces, end up with a shaped tool that has a more or less continuous working edge. That combination cores, flakes, and occasional bifacial pieces starts to look less and less like random breakage and more like an assemblage, a toolkit. But here's the tricky part. Nature also breaks rocks. And if you want to claim that something on an island that should never have been walked to is actually a human-made tool, you have to be absolutely obsessive about the difference. So how do archaeologists distinguish an artifact from a geofact, a naturally broken stone that just happens to look sort of intentional? They use criteria that have been tested and argued over for decades. Individual features matter: a clear striking platform, a bulb of percussion, ripple marks, the angle and symmetry of edges. A flake produced by controlled percussion has a diagnostic geometry that results from how elastic waves move through stone. It doesn't look like a frost-shattered chunk or a piece snapped off by rolling down a slope. Context matters too. One flake-like stone on a slope near a stream could be natural. 10 or 20 pieces displaying multiple diagnostic traits, made from the same raw material, sitting on the same ancient terrace surface, with cores showing repeated oriented removals that's different. The probability that random breakage would mimic a small workshop starts dropping fast. On Crete, survey teams reported exactly that sort of clustering. Repeated finds on specific terrace levels, associated with particular sedimentary units, rather than being scattered randomly across all surfaces. They weren't just picking up every odd-looking rock. They were mapping where those rocks appeared, how they were oriented, which raw materials they were made from, and what kinds of flaking they showed. There's another layer of complexity, though, and this is where the controversy really deepens. Most of these early tools from Crete are surface finds. They were picked up from exposed terrace surfaces and eroding gully walls not excavated from sealed, undisturbed layers with hearths and bones and clear stratigraphy. In archaeology, context is everything. A beautifully made hand axe with no secure geological context is a good story and a nice museum piece, but it's hard to date and harder to interpret. You can say that someone made it. You can't easily say when. So why do surface finds matter at all? Because on a landscape like southern Crete's, deep, undisturbed Pleistocene deposits are rare and hard to access. The processes that expose old terraces for you to walk on, uplift, erosion, river incision, are the same processes that strip away or disturb overlying sediments. If you insist on only accepting tools found in perfectly sealed layers, you might simply never see some of the earliest occupations. Surface assemblages, when they recur on the same geological features over wide areas, can still tell you things. They can map the distribution of activity across a landscape. They can be tied, with careful field geology, to specific terrace formations that have independent age estimates from dating the sediments, soils, or marine fossils within them. That's what researchers on Crete have tried to do. Link the tools to particular uplifted marine terraces and fluvial deposits whose ages can be bracketed by other methods. But the reliance on surface material also gives critics an easy line of attack. Eroded contexts mean that some stones could have moved from where they were originally dropped. Gravity, floods, landslides, even ancient farming and more recent construction can smear artifacts downslope or concentrate them in secondary positions. On an actively changing landscape, it's always possible to ask, are we looking at tools where they were used, or tools that have been redeposited and rearranged by thousands of years of geological processes? Southern Crete adds a further complication. The island is tectonically active. It's been rising relative to sea level in many areas, which is why those old marine terraces now sit well above the modern shoreline. Rivers have responded by cutting down through these uplifted surfaces, carving new gorges and leaving staircases of terraces at different heights. Each step in that staircase can represent a different phase of landscape evolution. Over hundreds of thousands of years, sediments laid down near the coast can be uplifted, eroded, reworked, and redeposited further inland or higher up the slope. So when you find a flaked stone on one of these terraces, you're not just asking, is this a tool? You're also asking, what episode of terrace formation is this surface actually part of? Has this particular piece moved from its original depositional context? How many cycles of erosion and redeposition has this landscape gone through since something with a brain last held this rock? Researchers working in the Plakias region have tried to tackle this with detailed geomorphology, mapping terrace levels, describing the sediments, comparing them to known sea level stands and regional uplift rates. In some cases they can say with some confidence that a given terrace surface dates to a particular Pleistocene highstand or river phase, perhaps on the order of 130,000 years old or older. Tools sitting stably on that surface weathered into it, matching its patina and degree of erosion, start to look like they've been there a very long time. But none of this is as clean as a buried campsite with a radiocarbon date. It's inferential. It leans hard on reading the landscape as a stratigraphic record, a tilted, broken, partially erased book where half the pages are missing. That's why the Cretan tools sit in this liminal space between startling discovery and ongoing argument. On one hand, multiple survey areas along the southern coast have produced consistent assemblages of what look very much like lower and middle Paleolithic tools, cores, flakes, and hand axe-like bifaces made from local raw materials found on geological surfaces that are plausibly 130,000 years old or more. On the other hand, the tools are mostly from surface contexts in a dynamic, tectonically active environment with plenty of opportunities for reworking and confusion. What everyone does agree on is that something at some point left intentionally shaped stone artifacts in those red and brown sediments above the Cretan shore. The real fight is over which episode in the island's long geological history those tools belong to, and by extension which hominin species could have been standing there, looking out over the same sea, deciding to cross or stay. To get at that timing, and at just how old really is in this case, we have to look closely at the dating methods that underpin the entire claim. How do you tell whether a stone lying on a terrace is 30,000 years old, 130,000, or 300,000? That's where the story turns from walking surveys and terrace staircases to the physics of electrons trapped in grains of sediment. When archaeologists say, 130,000 years, they're not secretly picturing a tiny calendar buried in the dirt next to a stone tool. They're almost never dating the artifact itself. What they're really dating is everything around it. The sediments, the landforms, the ancient shorelines and river deposits that tell you when that particular surface of the earth was last being built, flooded or buried. So on Crete, the key distinction is this. You can try to date the stone tool, or you can try to date the terrace it's sitting on. One of those is mostly impossible, the other is hard, but doable. Stone by itself is terrible for direct dating in this time range. It doesn't contain organic carbon, so you can't use radiocarbon. It often doesn't have the right minerals or alteration products for other direct methods. A flake of chert knocked off a cobble 500,000 years ago may look exactly like a flake knocked off last week, at least in terms of its internal chemistry. But that flake doesn't hang in empty space. It lies in or on sediments, gravel, sand, silt, soil that have their own clocks ticking inside them. Those clocks are what researchers lean on. On Mediterranean terraces, there are a few main lines of attack. The first is the oldest and simplest, stratigraphy, reading layers. If you stand in a gorge wall in southern Crete, you can literally see time stacked in bands of different coloured sediment. Coarse river gravels at the bottom, finer sands above, maybe a pale hardened soil on top, then another package of gravels cutting into that. Each unit represents a phase, a time when rivers flowed differently, sea level stood at a different height, or climate shifted from wetter to drier. Basic stratigraphic logic says lower is older, higher is younger, unless something has clearly flipped or folded the sequence. So if your tools consistently sit on a particular terrace level, capped by later deposits, you already know they must be older than whatever sealed them in. That's helpful, but older than X is not a date. To put actual numbers on those layers, archaeologists and geologists turn to more exotic clocks, methods that measure how long minerals have been exposed to light, or how long shells have been sitting in a slowly crystallizing crust. One of the big ones for Pleistocene sediments is OSL, optically stimulated luminescence. Here's the basic idea. Certain minerals in sand and silt, usually quartz and feldspar, act like tiny charge traps. Natural radiation from the environment knocks electrons around inside their crystal lattice, and over time, some of those electrons get stuck in defects. As long as the grains are buried in the dark, the traps keep filling. The longer they sit, the more electrons accumulate. But when those grains are exposed to sunlight, during transport by wind, waves, or rivers, the trapped electrons get released. The clock is zeroed. OSL dating works by collecting a sample from a sediment layer in complete darkness, then stimulating those grains with light in the lab and measuring the glow as trapped electrons are released. The amount of stored energy tells you how long it's been since those grains last saw daylight. In other words, how long since that layer was deposited and buried. If a terrace surface on Crete has an OSL date of, say, 140,000 years ago, plus or minus 20,000 years, that means the sands and silts on that surface were last reset by sunlight around that time, then covered and left in the dark. Artifacts lodged within that undisturbed layer should be at least that old, and probably not dramatically older. Another tool in the kit, especially near coastlines and in carbonate-rich environments like Crete, is uranium series dating. Uranium is a radioactive element that dissolves in water at low concentrations. When that water precipitates calcite, forming things like stalagmites in caves, travertine crusts or marine carbonate cements, the uranium gets locked into the growing crystal. Over time it decays into thorium at a known rate. Because thorium doesn't dissolve easily, any thorium you find in that calcite must come from uranium decay, not from the environment. Measure the ratio of uranium to thorium isotopes, do the math on the decay curve, and you can calculate how long that calcite has been sitting there crystallizing. On an uplifted marine terrace, you might date fossil coral, shells, or thin carbonate crusts that formed when the surface was close to sea level. If those give you ages around the last interglacial high stand, roughly 125,000 to 135,000 years ago, that anchors that particular step in the terrace staircase to a specific window in global sea level history. That's where terrace correlation comes in. The Mediterranean has been rising and falling with the ice ages like a giant, very slow tide. Global sea level was high at certain known times, low at others. If you can recognize a particular fossil shoreline, a wave-cut notch, a beach deposit with a specific assemblage of shells and match it to a global sea level high stand like marine isotope stage 5e, you can roughly say, this surface belongs to that episode. On Crete, researchers have mapped multiple levels of ancient shorelines and river terraces and tried to tie them into that global curve. If the tools are on a terrace that corresponds to a Ms 5e high stand, they're probably in the ballpark of 120,000 to 140,000 years old. If they're on an even higher, older terrace, they could be 300,000 years or more. None of these methods gives you a single magical number. Every date comes with uncertainty bars. An OSL result might be 132,000 plus or more to 18,000 years. A uranium series age might be 125,000 plus 10,000, 8,000 years. Terrace correlations might be looser still, likely MIS 5e, possibly MIS 7. Those plus or minus ranges matter. They're not just fine print. They're the difference between saying this almost certainly predates Homo sapiens in this region, and this could overlap with early modern humans. So when you hear around 130,000 years, you should translate that as somewhere within a bracket that might stretch from, say, 110,000 to 160,000 years, based on the best current data. It's a time window, not a birthday. What would really lock things down on Crete? First, truly in situ layers, tools found embedded in undisturbed sediments with clear stratigraphic relationships, lying on a dated surface, under another dated surface, with no signs of being churned by roots, burrows, or later erosion. A flake still half sticking out of a compacted horizon is more convincing than one lying loose on a weathered slope. Second, sealed contexts. Imagine a buried paleosol, a fossil soil, with artifacts resting on its top, then capped by a volcanic ash layer, or a carbonate crust that can be dated independently. If that cap is firmly pinned to 130,000 years, anything under it is older than that. That kind of stratigraphic sandwich is gold. Third, multiple independent dates converging. OSL on the enclosing sands, uranium series on a carbonate crust, maybe electron spin resonance on a fossil tooth in the same layer, all pointing to roughly the same time interval. When different clocks agree, confidence goes up fast. Critics of the Cretan claims focus on exactly these weak points. They ask, are the tools really in primary position, or could they have washed downslope from younger or older deposits? Are the terrace correlations solid, or are we forcing messy local geology into a neat global template? Were the OSL or U-series samples truly representative of the surfaces carrying the artifacts, or could small-scale erosion and redeposition have mixed old and young grains? One plausible error is reworking. A tool dropped 300,000 years ago on an older terrace could be freed by erosion and end up resting on a younger, 130,000-year-old surface. If you only date the younger surface, you might underestimate the artifact's age. The opposite can happen too. A younger artifact can be dragged into an older deposit by burrowing animals, root action, or small landslides, making it look more ancient than it is. Another possible problem is incomplete bleaching in OSL. If sediment grains weren't fully exposed to sunlight before burial, say, they were transported rapidly in a turbid flood, they might retain some memory from older exposures that can make a layer appear older than its true depositional age. U-series has its own traps, open system behavior, where uranium leaches in or out of the carbonate after formation can skew the apparent age. Terrace correlation can be thrown off by local uplift rates that differ from regional averages. This is exactly how skeptics work through such claims. They don't just say that can't be right because boats are hard. They interrogate the clockwork. They ask whether the dating methods were applied correctly, whether the geological interpretation is robust, whether the uncertainties have been fully accounted for. And they're right to, because if we're going to say that some non-sapiens hominin stood on Crete's shore 130,000 years ago, looking out at the horizon and somehow ending up on an island that had never been connected to the mainland, that conclusion is only as strong as the dates that put them there. Once you accept, even tentatively, that those terraces really do belong to that older Pleistocene world, a new question opens up. What exactly were those early visitors doing there? And what do their tools say about the minds and behaviours behind them? If you pick one of those Cretan tools up in your hand, it doesn't whisper a name to you. It doesn't say, "Hi, I'm Neanderthal," or "property of early Homo sapiens." What it does say very loudly is how it was made. And that's where archaeologists start. Broadly speaking, the tools being argued about on Crete fall into two overlapping technological stories. One is very old, the Acheulean tradition of big symmetrical hand axes and cleavers that stretches back more than 1,000,000 years in Africa and Eurasia. The other is more like what we see in Middle Paleolithic industries, the kind associated with Neanderthals and later archaic humans, where stone is managed in a more calculated piece-by-piece way. Neither label is perfect, but they help frame what we're actually looking at. Acheulean first. If you imagine the stereotypical Stone Age tool, you're probably picturing an Acheulean hand axe, a teardrop-shaped, carefully thinned, double-sided piece of stone that fits comfortably in the hand, with a sharp, continuous edge all the way around. They show up across Africa, the Levant, Europe, India, and beyond. On a map, they're like a fingerprint smeared across half the old world. Finding something like that on Crete is immediately interesting, because Acheulean-style hand axes aren't random rocks you bang together in 5 seconds. They take planning to make one. You don't just whack until you get lucky. You select a suitably sized cobble, often a particular raw material, like fine-grained chert or basalt. Then you work around it systematically. You knock off large flakes to rough out the shape. You flip it back and forth, alternating faces, trimming the edges, thinning the middle. Each strike is influenced by the last, and by where you want the next edge to be. That sequence, what archaeologists call a reduction sequence, is a kind of frozen thought process. It means the maker could envision a final form inside a raw lump of stone, hold that goal in mind through dozens of blows, adjust in real time as the rock behaved in unpredictable ways. So when people say hand axes imply advanced cognition, that's what they're talking about. Long-range planning, spatial visualization, fine motor control. But we have to be careful about what they don't imply. A hand axe by itself doesn't prove symbolic language. It doesn't prove modern consciousness. It doesn't even prove a particular species. Homo erectus made them, so did later archaic humans. So did early Homo sapiens in some regions. The cognitive baseline needed to produce a decent hand axe seems to have been shared across multiple hominin lineages. And complex is relative. Many modern humans today, if you drop them in a riverbed with some cobbles, couldn't produce a classic Acheulean hand axe on the first try. Skill doesn't map cleanly onto species labels. Now shift to the other story, the more Middle Paleolithic style ways of working stone. Here, the star of the show isn't a single big tool, but the way flakes are struck from a core. We're talking about prepared core technologies like levoloi and related strategies. Instead of randomly detaching flakes until something looks usable, the napper shapes the core itself into a kind of stone machine designed to produce one or more flakes of a fairly predictable size and shape. To do that, you have to prepare a convex surface, trim the edges to control how force will travel, identify a striking platform, then hit in just the right place and direction to send a flake rippling across the surface. When it works, you get a flake that can be used immediately as a knife or further modified into a point or scraper. And if you repeat the sequence in a standard way, you get multiple similar flakes from one core. On Crete, some of the artifacts appear to fall closer to this prepared core world than to the old heavy Acheulean style. That's important, because Middle Paleolithic style technologies are often associated with more flexible, task-specific toolkits and more intensive planning. You're not just making one big multi-purpose hand axe, you're making a series of different tools, each optimized for certain jobs, cutting meat, scraping hides, shaping wood. So what does that tell us? Again, not a simple label like Neanderthals were here, but it does point to people who were organizing their work in more modular, anticipatory ways. They were thinking not just in terms of I need a sharp edge now, but I will need different edges later, and here's how I'll get them out of this lump of stone. Now zoom out from individual tools to the whole assemblage. Archaeologists don't just pick up the prettiest pieces and call it a day. They try to reconstruct entire reduction sequences from what's left on the ground. Cores, flakes, broken bits, exhausted tools. That debris can tell you a surprising amount about how people moved through the landscape. If you find big, heavy cores being roughed out near raw material sources, and only lighter finished tools carried onto high terraces or far inland, that suggests a mobile group managing weight. They're minimizing what they lug around. If, on the other hand, you see full reduction sequences everywhere, the whole chain from first flake to tiny resharpening scars, that might mean people were spending longer at particular spots, doing most of their work on site. Raw material choice adds another layer. If the Cretan tools are almost all made from local beach cobbles or nearby outcrops, that fits with short-range movements. People are probably foraging within a relatively small radius. If you start finding tools made of exotic stone, specific cherts or radiolarites that only occur tens or hundreds of kilometers away, you suddenly know these weren't just casual wanderers. They either travelled long distances themselves, or were linked into networks that moved materials and ideas over big areas. Even the intensity of use is a clue. When cores are worked down to tiny exhausted nubs and flakes are resharpened until they're almost unusable, that often means people were operating far from raw materials, squeezing every last edge out of what they had. On an island like Crete, where good stone might not be everywhere, that pattern would make sense. But here's where things get messy, and why this debate about who is so hard. Stone is a very conservative medium. There are only so many efficient ways to break a rock to get a sharp edge. Different hominin groups, separated by time and geography, can independently arrive at similar solutions. Convergent evolution applies to technology too. A Neanderthal, an early Homo sapiens, and a late Homo heidelbergensis might all pick up the same kind of cobble and produce broadly similar flakes if they face the same constraints. So this looks Middle Paleolithic is not the same as this was definitely made by Neanderthals. That's why archaeologists talk about traditions and modes instead of species-specific brands. Acheulean, Mousterian, Middle Stone Age. These are technological umbrellas, not genetic ones. So how do they compare assemblages cautiously? They look for recurring signature traits, but treat them as probabilities, not certainties. Things like the prevalence and type of prepared core strategies, classic Levallois, or more ad hoc variants, the proportion of big bifaces like hand axes versus smaller retouched flakes, the way edges are modified, fine invasive retouch or coarse scalar scars, the organization of the toolkit, many specialized tool types or a few generalist forms, the patterning in raw material use and reduction intensity. If a set of tools from Crete shares a cluster of features that strongly resembles, say, Middle Paleolithic assemblages from mainland Greece or the Levant, that raises the likelihood that the same kind of makers, or at least closely related technological communities, were involved. But because similar looks can be produced in different contexts, responsible researchers frame those links as affinities, not identifications. So when you hear something like the Cretan assemblages show Acheulean affinities or have Middle Paleolithic-like characteristics, translate that as the way these stones were broken and shaped fits best with toolkits we usually associate with certain time periods and hominin populations elsewhere, but we cannot, on that basis alone, pin a specific face to the maker. All of this brings us back to the bigger puzzle. The tools speak of planning, of mobility, of people who understood raw materials and landscapes well enough to exploit them efficiently. But they don't come with a passport. To figure out who could have carried that knowledge across open water, we have to step away from the stones for a moment and look at the sea itself. What kind of Mediterranean world existed around 130,000 years ago? And what opportunities or barriers it might have presented? To understand that world, we have to drop ourselves into a very particular moment in Earth's mood swings. About 130,000 years ago, the planet was sliding into what geologists call the last interglacial, also known in Europe as the Eemian, and globally as marine isotope stage 5e. Names don't matter much here. What matters is what it felt like to live through. Compared to the glacial periods before and after, this was a warm spike. Ice sheets in the northern hemisphere pulled back. Sea levels rose, probably several meters higher than today at peak. Forests crept north into regions that had been tundra. In many places, climates were not just warmer, but wetter, more stable, more predictable. But stable in geological language doesn't mean unchanging on the ground. When you zoom in from the 100,000-year scale to the 1,000-year scale, or the human lifetime scale, this so-called interglacial was still full of swings. Rain belts shifted. Storm tracks wandered. Coasts eroded and rebuilt. Rivers changed course. A shoreline that looked one way when your grandparents were born might look very different by the time you had grandchildren of your own. In the Mediterranean, that dance was especially intense. This basin sits at the intersection of African monsoon systems, Atlantic westerlies and Eurasian continental climates. Small nudges in global temperature can radically alter how those systems interact. During the last interglacial, large parts of the Mediterranean world seem to have been greener than in the harsher glacials. More woodlands, richer grasslands, more reliable freshwater in many coastal zones. From the point of view of a Pleistocene forager, that's opportunity. Imagine moving along a coastline where you have, in a relatively narrow strip, terrestrial game moving between inland pastures and the sea, freshwater outlets where fish gather seasonally, rocky shores crowded with shellfish and limpets, sandy beaches where sea turtles haul out to lay eggs, occasional strandings of dolphins or whales after storms compared to the deep interior. Where droughts could turn a good valley into a death trap, coasts are shock absorbers. They buffer climate variability. When land animals are scarce, you can dig clams. When the sea is rough, you can hunt in the brush behind the dunes. The menu is broader, the risks slightly lower. This is part of why archaeologists talk about coastal adaptations as such a big deal in human evolution. Not because early coastal people were magically smarter, but because the shoreline forced them or allowed them to develop new behaviours. You need to understand tides, seasons and storm patterns. You need to time your visits to rocky platforms so you're not cut off and drowned. You may need new tools for prying, scraping, cutting. You may need containers to haul water and shellfish. And if you're clever, you start to see the coastline not as a dead end, but as a highway. Walkable, flat terrain. Predictable sequences of bays and headlands. Bays that funnel fish, estuaries that trap nutrients, predictable landfalls where fresh water and shelter tend to coincide. Now put that highway into its last interglacial context. Sea level at the warmest part of that period was probably higher than today. But it didn't sit at one exact level for the whole time. It rose, it paused, it maybe fluctuated a bit with shorter-term ice dynamics. On top of that, the local picture around any given island, including Crete, was modified by tectonics. Some stretches of coast are being slowly uplifted. Others are subsiding. What that means is the distance from mainland to island, the number of stepping stone islets, the shape of bays and channels, those things were not fixed. They changed over tens of thousands of years, and sometimes over much shorter intervals. During colder glacial phases when sea levels dropped by 100 meters or more, vast shelves that are underwater now would have been dry land. Islands would have swollen, seafloors would have turned into plains and valleys. But even then, Crete seems never to have connected directly to the mainland. There was always some water barrier. The question is, how wide, how rough, how intimidating? Around 130,000 years ago, during this warm phase, the picture was different again. Sea levels were high, some of those potential land bridges were drowned. But remember, sea level is an average. Local uplift could have raised parts of Crete. Regional differences in bathymetry mean that even with high global seas, certain shallow banks might have sat just below the surface, calming waves and creating calmer channels. From a hominin's point of view, standing on a headland in, say, southern Greece or southwestern Anatolia, the horizon might have shown more than just empty water. You might see a faint dark smudge on a clear day. You might see bird flight paths that suggested land out there. You might watch pumice rafts drifting from volcanic eruptions, or floating logs riding currents in a particular direction, hinting that the sea itself had lanes. Climate swings don't just reshape coasts, they reshape movement. When interior regions dried, people would have hugged rivers and lakes. When grasslands expanded, overland migration corridors opened up between Africa, the Levant and Eurasia. When sea levels rose and shorelines stabilized, coastal routes would have become more attractive, predictable food, easier walking, fewer defiles and mountain passes to navigate. The Mediterranean at 130,000 years ago was likely threaded with such corridors. Not roads, obviously, but chains of habitable nodes. River mouths, lagoons, sheltered coves with freshwater springs. Once any hominin population became comfortable living along those edges. Once they learned that you can live for months or years harvesting shellfish, fish, seabirds, and stranded mammals without starving. The map changed. The sea stopped being a border and started being a membrane, thin, permeable, potentially crossable in the right conditions. Coastal life, in that sense, is a kind of training ground for maritime thinking. If you know that storms throw dead whales onto your beach from far offshore, you know the ocean moves things. If you learn that certain pieces of driftwood, logs, or mats of vegetation can support weight, you start to grasp buoyancy, whether you have a word for it or not. If you see seabirds commuting in straight lines at dawn and dusk, you infer commuting routes. If you return to the same headland year after year and always see the same faint line of land on the horizon, your mental map begins to include places you've never set foot on. All of that becomes more pressing when you're living in a world that doesn't sit still. Interglacial warmth might make the coast rich, but it can also raise the sea slowly under your feet. A camp spot that was comfortably inland for your grandparents might be at the cliff edge for you, and in the surf for your grandchildren. Dunes shift, beaches erode, caves flood, safe freshwater sources get salinized. So coastal groups had to be mobile and observant. They had to notice when a sandbank was disappearing, when a lagoon was opening to the sea, when a once dry lowland began to salt up. They had to be able to shift camps, abandon favourite sites, and search for new ones. That movement is exactly what erases their traces. Most of the really attractive coastal real estate from 130,000 years ago, the low, flat platforms near river mouths, the gentle bays, the shallow estuaries, is now underwater. When global sea level rose at the end of later glacials, it drowned those landscapes. Whatever hearths, butchered bones and stone scatters were there are now under meters of water and sediment. On land, the story isn't much kinder. Wind repeatedly reworks coastal dunes. Storm waves chew away at cliff-top sites. Cemented beach deposits slump and collapse. If you do get a preserved surface, it might be buried under thick colluvium or sliced by later erosion so that only fragments remain. That's why the archaeological record of early coastal life is so patchy. It's not because coastal living was rare, it's because coastlines are dynamic, and the nice parts are exactly the bits most likely to be destroyed or submerged. So when a few stone tools turn up on a high terrace in Crete, they're not just isolated curiosities. They're like shouts from the tiny, tiny fraction of coastal history that happen to land in a stable spot, get lifted by tectonics or locked into cemented beach rock, and then be exposed again without being obliterated. Now fold all of that back into the question of windows of possibility for reaching islands. If you graph sea level, climate, and human presence over time, You don't get one neat horizontal line of could cross or couldn't cross. You get pulses. Times when populations were dense enough in coastal corridors to generate experimentation. Resources inland were stressed enough to push people into new habitats. Coasts were configured in ways that reduced effective crossing distances or made targets visible. Storms, currents, and winds aligned to increase the odds that floating logs, debris, or unlucky, but living passengers might be carried from one landmass toward another. A window of possibility isn't necessarily long. It might be a few centuries when climate, coastline, and population distribution align in just the right way. It might open and close multiple times around the last interglacial. Most of those openings would leave no obvious mark. One or two might leave a scatter of tools on what later became a high, fossil shoreline in Crete. During a warm, resource-rich interglacial, groups along the Aegean or Libyan coasts could have developed very sophisticated coastal foraging. They might have been following migrating fish runs, bird routes, or seasonal shellfish peaks up and down the shore. They might have been camping on promontories facing visible islands for generations, watching the same cloud caps form over them, the same birds fly to and from them. At some point in one of those windows, somebody ends up on a floating mat of vegetation torn loose by a flood, or on a fallen log that doesn't sink, or on a deliberately lashed-together raft of reeds and timber. Maybe it's a single family, maybe it's half a band, shoved offshore by a storm surge in the middle of the night. Maybe it's a more intentional thing, pushing off from a calm, sheltered bay during a lull in the wind, following birds and the setting sun toward a faint smudge. The interglacial Mediterranean doesn't guarantee such a crossing, it just makes it slightly less insane. Warmer water, more predictable wind regimes, stable seasonal cues, rich resources on both sides of the water gap, they all soften the edges of what would otherwise be a lethal gamble. They also raise the odds that if someone did make it across, they would find enough food to survive, enough fresh water to hang on, and enough raw material to make tools like the ones we now puzzle over. And because so much of that shoreline world is gone, drowned, eroded, rearranged, the only hints we may ever get of those brief windows are scattered stone artifacts in unlikely places. Which brings us back to the real question. If the Mediterranean, around 130,000 years ago, occasionally opened these windows, if it sometimes turned islands like Crete from unreachable specks into barely plausible destinations, who, exactly, was in a position to step through? To answer that, we need to be very clear about one thing. If these tools on Crete really are about 130,000 years old, they do not belong to us. At that time, fully anatomically modern humans were probably just beginning to stir in Africa. There are hints of early Homo sapiens in the Levant a bit later, but the big, sustained out-of-Africa wave that populates Eurasia doesn't kick in until around 60,000–70,000 years ago. So if somebody was already poking around an island in the middle of the eastern Mediterranean tens of thousands of years before that, we're not looking at your direct, unbroken sapiens cousins. We're looking at their older, stranger relatives. The usual shortlist of suspects runs like this: Neanderthals. Homo heidelbergensis, like populations often called archaic Homo or Middle Pleistocene hominins, and a grab bag of regional forms in that same archaic grade, some named, some only hinted at in the bones and DNA. None of these were primitive cavemen in the cartoon sense. They were humans in the broader sense, big-brained, tool-using, social mammals who had already survived multiple glacial interglacial swings before the last interglacial even began. Start with a celebrity, Neanderthals. By 130,000 years ago, classic Neanderthals were already established across much of Europe and Western Asia. Their fossils show up from Spain to the Caucasus, from France down into the Levant. They hunted large game, handled harsh winters, and, as we saw, developed sophisticated tools and social behaviour. What about the Aegean and Eastern Mediterranean? We don't have a Neanderthal skeleton from the Greek mainland that dates neatly to exactly 130,000 years ago. But we do have Neanderthal remains and tools in Greece from before and after that window. We have them in Italy, we have them hugging the coasts of the Mediterranean in multiple places. Their range absolutely comes close enough that a coastal Neanderthal group could have been looking out over the same waters that separated Crete from the mainland. Then there's Homo heidelbergensis and its kin. Heidelbergensis is a bit of a catch-all term. It usually refers to robust, big-brained hominins living roughly 600 to 200,000 years ago across Africa and Eurasia. Many researchers think European heidelbergensis populations gave rise to Neanderthals. African ones fed into the line that became modern humans. Eastern ones may have contributed to Denisovans. By 130,000 years ago, pure heidelbergensis in Europe might have already been morphing into early Neanderthals. But in southeastern Europe and the eastern Mediterranean, we have fragmentary fossils that look intermediate, archaic, not quite Neanderthal, not quite sapiens. Think of them as late heidelbergensis-grade hominins, stocky, tough, already able to handle variable climates and shifting landscapes. These populations were around in Greece and the Balkans before 130,000 years ago. Some might have persisted regionally as relic groups into the last interglacial. Their stone tools were broadly Acheulean and Middle Paleolithic hand axes, transitioning toward more refined flakes and points. Nothing about that toolkit screams ocean voyages, but nothing rules out coastal living either. And then there are the murkier figures. We know Denisovans mainly from Asia, but the genetic story suggests a whole constellation of regional archaic groups, some of which interbred with Neanderthals and the ancestors of modern humans. The eastern Mediterranean sits at the crossroads of these lineages. It's very likely that over hundreds of thousands of years, the area saw waves of archaic Homo coming out of Africa, others coming down from Eurasia, some mixing, some going extinct. The fossil record doesn't list all their names, it just tells us more than one kind of human lived in that broader region before modern humans did. So when we ask who could have made it to Crete, we're really asking which of these overlapping, partially known hominin populations was coastal, clever and unlucky or bold enough to end up offshore. To answer that, we have to talk about ranges and about gaps. We know Neanderthals used caves along coastal Spain, Italy and Israel. We know archaic hominins were in Greece and the Balkans earlier. We know Homo erectus and later forms reached places like the island of Flores in Indonesia by at least 700,000 years ago, which implies some kind of water crossing long before Crete enters the picture. But we don't have Neanderthal bones on Crete. We don't have Heidelbergensis bones. We don't have any hominin bones at all from those Pleistocene coastal terraces. Does that absence mean they weren't there? Not really. Bones are fragile. They rot, dissolve, get chewed up on an actively rising, eroding, wave-lashed island. The odds that a small band of early visitors would leave behind a nicely buried skeleton that then survives intact for 130,000 years, then happens to be exposed in exactly the right place for a modern archaeologist to spot it, that's astronomically low. Even in parts of the world where we know Neanderthals lived in big numbers for a long time, we often have only a few dozen individuals represented. The fossil record is like a lottery where most winning tickets fall in the ocean or burn in a fire. The fact that Crete hasn't yet produced a skull doesn't tell us much, except that we haven't been incredibly lucky there. Stone tools, by contrast, are durable. A flake of chert doesn't care if a wave hits it. A hand axe doesn't dissolve if a dune shifts. When we find a scatter of artifacts on a high ancient shoreline, we're not seeing the one place people ever lived. We're seeing the one place where an almost indestructible part of their life happened to get locked into rock. That's why archaeologists are cautious about using absence as evidence. No fossils on Crete doesn't mean no hominins. it means we're working with half a sentence torn from a book that's mostly underwater. So instead of asking, who do we have bones for on Crete, we ask whose known behaviour and known range makes them plausible visitors. This is where we have to distinguish between what's directly evidenced and what's inferred. We have direct evidence that Neanderthals used coastal resources in places like Gibraltar and Italy. We've got marine shells, fish bones, seal remains associated with their tools and occupation layers. We have evidence that they were capable of planning hunts, hafting tools, managing fire, perhaps even gluing stone to wood with complex resins. That all points to high-level cognition and a capacity for planning. Do we have direct evidence of Neanderthals building boats? No. There's no Neanderthal canoe preserved in some miracle bog. But if they were comfortable working wood, reading coastlines and timing movements around tides and seasons, it's not a huge leap to imagine them experimenting with floating logs, rafts, or simple watercraft. For Heidelbergensis grade groups in the eastern Mediterranean, the evidence is sparser. We have hand axes and flake tools. We have occupation sites in caves that were probably not far from ancient shorelines. We infer that they too followed rivers and coasts, because almost all hominins do water and food cluster there. But we don't yet have the smoking gun of systematic shellfish harvesting or clear maritime specialization. Then there's a more basic behavioral capacity, dispersal. Every hominin that left Africa had to be capable of long-range movement, flexible diet, and some level of social organization. Erectus did it. Heidelbergensis and its descendants did it. Denisovans and Neanderthals did it. That shared, deep capacity for pushing into new environments is arguably older than any named species on our list. If you give such a population a Mediterranean full of coastal corridors, visible islands, and occasional extreme storms that rip chunks of forest into the sea, you don't need them to be master shipwrights. You just need them to do what hominins constantly did: range, explore, take risks, sometimes by choice, sometimes by accident. So we end up with a strange asymmetry. On Crete, we have technology without bodies, stone tools that say human very loudly, but no skeletons to match them too. In the broader region, we have bodies without boats. Neanderthals and archaic Homo in caves and rock shelters, leaving us tools, bones, hearths, but no preserved rafts, no paddles, no piers. Somewhere between those two absences lies the truth. Maybe Neanderthals along the Greek coast built simple rafts, and a few crossings to Crete worked by luck and timing, leaving only a handful of tools. Maybe late Heidelbergensis-like groups were the ones hugging those shores earlier, pushing out in fits and starts when shorelines were different, when the gap to Crete was narrower or calmer. Maybe multiple hominin populations at different times touched the island's edges, each leaving a thin archaeological whisper. What we can say is this: whoever reached Crete had to share a certain behavioral profile. They had to be comfortable with coastal living. They had to understand seasonal patterns well enough to survive on an island's limited resources. They had to manage tools, fire, and social cooperation robustly enough to make an accidental landfall into a sustainable existence. Neanderthals fit that description. So do some Heidelbergensis-grade archaics. So might other, less well-known hominins that passed through the eastern Mediterranean and left only fragments of their story on the mainland. The hard part is that, for now, the tools on Crete won't tell us whose hands held them. They just tell us that somebody did something in the eastern Mediterranean far earlier and in a more maritime way than our standard story expects. To narrow the suspects list, we have to ask a more focused question. Among these candidate hominins, who do we know was already flirting with the sea elsewhere? Who, beyond Crete, shows the kind of behaviour that might spill over into true sea crossings? That's where Neanderthals step back into the spotlight. So let's follow them to the water's edge. If Neanderthals or their close archaic cousins really were the ones flirting with Crete, we'd expect to see hints of that behaviour elsewhere. Not a fossilised boat with property of Clan Zog carved into it, but scattered clues along other coasts and islands that something more than simple beachcombing was going on. Start with the more modest islands, the ones close enough to the mainland that, on a clear day, you can stand on the shore and actually see them. In the Ionian Sea, off western Greece, there's the island of Lefkada and a chain of smaller land masses. Some of these might have been connected to the mainland during very low sea levels, but others almost certainly remain cut off by at least a few kilometres of water. Archaeologists have found Middle Paleolithic stone tools there, flakes and points very much in the Neanderthal style. Similar stories pop up around the Aegean. On islands like Naxos and perhaps even on now submerged plateaus, we find tools that look, technologically, like what Neanderthals and contemporaries were making on the mainland at roughly the same time. The same manufacturing techniques, the same types of points and scrapers, the same patterns of use wear. It looks like the same people, just offshore. Then there's the Strait of Gibraltar. On the European side, Neanderthals used caves that opened directly onto the sea. At sites like Gorham's Cave, we find clear evidence of marine exploitation. Limpets, mussels, fish, even seal bones associated with Neanderthal layers. On the African side of the strait, we have roughly contemporary sites that also show Middle Paleolithic toolkits and coastal adaptation. The water gap between the two shores is about 14 kilometres at its narrowest. Strong currents, unpredictable winds, not an easy paddle. But if you draw a circle around Neanderthal sites in southern Spain and North Africa, the Strait of Gibraltar sits right in the middle. It looks less like a boundary and more like an obstacle they may, at least occasionally, have tried to cross. Farther east in Italy we see something similar. Neanderthal groups occupy caves along the Tyrrhenian and Adriatic coasts. At some sites they leave behind heaps of shellfish remains that suggest regular harvesting, not just the odd beach snack. In Israel and Lebanon, coastal caves show Neanderthals exploiting fish and marine mammals alongside terrestrial game. None of these cases is a smoking gun for open water voyages. They don't show us Neanderthals Island hopping across the Mediterranean like Bronze Age traders. But together they sketch a portrait of a hominin very comfortable at the shoreline, a species that knew tides, red currents, and was used to planning around the rhythms of the sea. That brings us to a crucial distinction. When does being coastal become being maritime? Archaeologists usually think in terms of three rough categories. At the simplest level, you have shoreline opportunists. These are groups that live near the coast, occasionally gather shellfish, maybe scavenge the odd beached whale, but don't really specialise in marine resources. A riverbank hunter who eats a few clams a year counts as coastal but not maritime. Next, you have systematic coastal foragers. These are people who regularly harvest shellfish, fish in shallow waters, and maybe venture a bit offshore on foot, wading, reef walking, using simple nets or traps. Their diet and technology show a clear, ongoing engagement with the sea. Finally, you have true seafarers. These are groups that intentionally build watercraft, plan crossings to places they can't see both sides of at once, and treat water as a highway rather than a barrier. Reaching an island like Crete, which was never fully connected to the mainland during the relevant periods, almost certainly falls into this third category. So where do Neanderthals land on that spectrum? The cautious answer most researchers would give is somewhere between stage 1 and stage 2, with a few hints of something more. At Gibraltar, for example, the sheer volume of limpets and mussels suggests not just random snacking, but organised collecting. In Italy, cut marks on seal bones show butchery of marine mammals that would have required observation of their behaviour, and perhaps coordinated hunts along rocky shores. At some Levantine sites, fish bones indicate regular consumption, not just occasional scavenging. Taken together, those lines of evidence push Neanderthals solidly into the systematic coastal forager category. They knew how to exploit the marine margin efficiently. They weren't afraid of the water, but intentional seafaring is another step. It means deliberately leaving land behind. How do we tell archaeologically when that step has been taken? One blunt criterion is geography. If hominins are on an island that was never fully joined to a mainland, or that was separated by deep channels even at the lowest ice age sea levels, something had to carry them there. You can argue about timing and species, but not about the need for some kind of crossing, intentional or accidental. Another clue is patterning. If you find one lonely site on an island edge with a tiny scatter of tools and nothing more, you might be looking at a one-off event, an accident, a drift, a storm-tossed log. But if you find multiple sites spanning different time periods, deeper inland, with clear signs of repeated occupation, then you're probably not dealing with a single freak storm. You're looking at intentional traffic. This is where experimental archaeology enters the picture. Over the last few decades, several teams have tried to test just how hard early seafaring would have been for hominins with Neanderthal-grade technology. No metal tools, no sails, no neatly planked hulls, just wood, vines, hides, maybe some stone adzes or hand axes. The results are humbling in both directions. On one hand, very simple rafts built with Stone Age techniques can be surprisingly seaworthy. Lash a few large logs together with plant fibre, wedge some cross pieces for stability, maybe add a raised platform to keep your supplies dry, and you have a raft capable of carrying several adults across short to moderate distances, even in choppy conditions. Experimental voyages in the Aegean and near Gibraltar have shown that, with favourable currents and basic paddling, such rafts can cover 10 or 20 kilometres in a matter of hours. No advanced carpentry, no deep theoretical understanding of buoyancy, just observation, trial and error, and a willingness to get wet. On the other hand, controlling where you end up is much harder. Without a sail or a deep keel, you're at the mercy of wind and current patterns. Steering is crude, landing where you intend, as opposed to wherever the sea decides to spit you out, takes practice and some level of accumulated knowledge about local conditions. So experimental archaeology tells us two things at once. First, Neanderthal-level technology is absolutely sufficient to build watercraft capable of crossing the sort of channels that separate many Mediterranean islands from the mainland. You do not need modern humans or Upper Paleolithic blade tech for that. Second, doing it reliably on purpose, over and over again, probably requires a cultural tradition of seafaring. Shared knowledge, stories about winds and currents, perhaps specialized roles within the group. That's less about hand axes and more about social learning. This is exactly where scholars begin to argue. Skeptics of Neanderthal seafaring point out that, aside from a handful of contested islands, Neanderthal archaeology overwhelmingly hugs the mainland. They see coastal sites, yes, but not a clear, repeated pattern of offshore colonization. They emphasize the difficulty of navigation without maps or compasses, the dangers of open water, the lack of preserved boats. More cautious proponents counter with 3 points. First, the preservation problem. Boats and rafts made of wood, reeds or hides almost never survive for 100,000 years, especially in dynamic coastal zones. Expecting a Neanderthal canoe to wash up intact in the archaeological record is unrealistic. Second, the analogy problem. We know that much earlier. Hominins, Homo erectus grade populations somehow reached islands like Flores in Indonesia by 700,000 years ago. Whatever carried them there wasn't rocket science. If erectus could manage at least occasional crossings in Southeast Asia, it's hard to argue that later, bigger-brained Neanderthals were categorically incapable of similar feats in the Mediterranean. Third, the behavioural envelope. As we saw, Neanderthals planned hunts, hofted tools, used complex adhesives, buried their dead, and may have used pigments and engravings. That's a cognitive and cultural package fully capable of experimenting with floating logs, stitched together reed bundles, or hide-covered frames. The debate, then, isn't really could they ever get on a raft. It's how often did they do it and under what circumstances. For some researchers, the default model is this. Neanderthals and other archaic hominins were primarily land-based, with occasional rare water crossings driven by accidents or extreme curiosity. Islands like Crete, if reached before sapiens, were statistical flukes, not part of a broader maritime tradition. Others see a more systematic pattern emerging. They note archaic tools on multiple islands in the Aegean and Ionian seas, potential crossings at bottlenecks like Gibraltar, and the Flores precedent in Indonesia. To them, early seafaring looks less like a one-time miracle and more like a repeated, low-frequency behaviour whenever the right combination of coasts, visible islands, and curious hominins came together. Where does Crete fit into this? It's one of the hardest cases because its separation from the mainland is substantial. You can't just wade it, and even at the lowest sea levels, you're looking at deep channels and multi-hour crossings. If Neanderthals or their relatives reached Crete around 130,000 years ago, it pushes them closer to the true seafarer end of the spectrum, at least in that region and moment. And that raises the stakes. If you accept Neanderthals as capable of that kind of crossing, you have to expand your sense of what their world looked like. Their maps weren't just rivers and valleys. They included islands, straits, and coastal routes that our fossil record barely hints at. If you reject that capability, you're forced to look for other explanations. Misdated tools, misinterpreted geology, or some other, as yet unidentified hominin, with a surprisingly wet set of habits. To sort between those options, we have to get even more specific. How exactly would anyone, Neanderthal or otherwise, have made the jump from mainland Greece to Crete? What do currents, wind patterns, and paleogeography actually allow? And does that tilt the scales toward accident or intention? To answer that, we need to sketch the ancient seascape the way they would have experienced it, not as a satellite image with neat bathymetric contours, but as a series of horizons, silhouettes, winds, and currents. Start with the big picture. During the glacial periods relevant to these tools, roughly the last 200,000 or 300,000 years, sea levels in the Mediterranean were often tens of meters lower than today, sometimes over 100. Exposed continental shelves would have pushed coastlines outward, turning parts of today's sea floor into dry land. Headlands would have extended farther, bays would have been narrower, and some islands would have been closer to the mainland, or even joined to it. Crete, though, is different. It sits on its own block of crust, separated from mainland Greece by deep basins. Lower sea levels shrink the gaps a bit. They don't erase them. You can make the crossing shorter, not trivial. Instead of one vast, unbroken channel, you get a series of narrower passages, promontories, and crucially intermediate islands and banks that might appear, or at least come closer. Imagine standing on a glacial age coast in southern Greece or the Peloponnese. The horizon is not empty. To the south and southeast, especially on clear, dry winter days, you might see faint smudges of land. Not crisp outlines like a postcard, but dim shapes that flicker in and out of view with haze and humidity. Farther out, even if the island itself is below the curve of the earth, clouds could gather over its mountains, hinting at land where none seems visible. Seafarers today still use cloud islands as a cue. Closer in, things get more manageable. Between mainland Greece and Crete lies a loose chain of land masses and submarine highs, the Cyclades to the east, the smaller islands and banks of the southern Aegean, the arc of what is now Kythera, Antikythera, and western Crete. At low sea levels, some of these would have been larger, some joined, some transformed from reefs into real stepping stones. You don't need to know their exact outlines to see the pattern. A determined coastal people could plan the journey as a series of short hops rather than one heroic leap into featureless blue. But what counts as a short hop when you have no compass, no charts, and a boat that's basically a bundle of logs? For a modern kayaker, 10 kilometres of open water is a workout. For a group on a heavy, awkward raft with no efficient paddles, that same distance could mean hours of slow, grinding movement, especially if the wind isn't helping. And that's the next piece of physics, the Mediterranean itself. The surface circulation in this basin is not random. Broadly, water flows in from the Atlantic at Gibraltar, sweeps eastward along the North African coast, loops around the Levant, then comes back west along the southern arc of Turkey and Greece. Superimposed on that are local gyres, wind-driven currents, and seasonal reversals. In the Aegean, prevailing winds, especially the strong summer meltemi from the north, could push floating objects southward. A log, a cluster of vegetation, or a primitive raft that drifted free off a Greek headland might not just bob in place. It would be carried, slowly but relentlessly, toward the southern islands and eventually toward Crete. Add waves and weather, and you get something like a conveyor belt with turbulence. Not predictable in fine detail, but biased enough that away from the mainland is a real direction. Now add human agency. Hominins watching the sea day after day would have noticed which way debris moved. They'd see where foam lines formed, where fish gathered, how driftwood piled up on certain beaches after storms. Over generations this becomes knowledge. The water here takes things that way. The wind there helps you come back. Visibility plays into that. On some days, Crete or its nearer satellites would have been clearly visible from certain promontories on the mainland when the atmosphere cooperated. On others, they'd disappear into haze, a group that had already made short experimental trips offshore, following fish, testing rafts, rescuing beached logs might start connecting the dots. There's land out there. Things that float here end up there. What could they actually float on? This is where the minimal technology scenarios matter. We don't need to assume planked boats or complex carpentry. The bar for crossing a few tens of kilometres of relatively sheltered sea is much lower. Picture three broad categories. First, the simplest, opportunistic flotation. Large logs rolling down rivers after floods. Natural rafts of vegetation torn from riverbanks. Tangled mats of reeds and branches. A single individual or a couple of kids might climb onto these things just for play, or in an emergency and realize this floats and it moves when we paddle. Next, deliberate rafts. Take that insight and add Stone Age engineering. A few straight logs trimmed with stone tools, crosspieces wedged in place. Vines or inner bark used as lashings. Maybe a layer of brush or reeds on top to keep feet above the waterline. No advanced joinery, just persistence. Even basic experimental builds today, using replica stone tools, can produce stable platforms capable of carrying several adults and some cargo. Finally, proto-boats. Here we're in more speculative territory, but still well within what's been demonstrated ethnographically and experimentally. Bundles of reeds tied into cigar-shaped floats, lashed together into a boat like hull. Or a light framework of branches smeared with animal skins and fat to shed water. These kinds of craft are wonderfully buoyant, but not very durable. They leave almost nothing we'd find after 130,000 years. Yet they can cross surprising distances, especially if you're not in a hurry. None of these require metallurgy, wheels, or agriculture. They require an eye for materials, patience, and a culture that tolerates a certain amount of trial and error at the water's edge. But a raft is only half the story. The other half is who gets on it and why. Group size is crucial. A single storm-blown individual clinging to a log might indeed wash up on a new shore. But one unlucky castaway does not create an archaeological record that spans multiple sites and time periods. They probably die without reproducing, or they live out their life as a strange, isolated anomaly. To leave a real footprint, you need groups, several individuals at once. Ideally mixed ages and sexes, enough genetic and social diversity to function on arrival. That means bigger, more stable craft. It means trips that are at least somewhat planned, bringing tools, fire, maybe water and food. It suggests people who don't just fall into the sea by accident, but step onto something that's meant to float. And it implies repeat crossings. Think about it from the perspective of the people who stayed behind. If a daughter, a brother, and 3 hunting partners paddle away toward that hazy line on the horizon and never return, that's a tragedy. It doesn't become a tradition, it becomes a cautionary tale. Don't go that way. For seafaring to become part of a group's behavioural repertoire, some trips must succeed. People have to leave and then come back with stories, with resources, maybe with mates or alliances. There is land over there. There are animals. There is fresh water. Here is how the winds shift in the afternoon. Only then do you get what archaeologists call sustained presence. Multiple occupations, tool scatters inland, patterns that say, we didn't just wash up here once. We came back. We taught our children how to get here. So why take the risk in the first place? From a purely actuarial standpoint, venturing out onto deep water in a flimsy craft is a terrible idea. The sea is unpredictable. Weather changes quickly. The cost of a mistake can be everyone on board. But evolution doesn't optimize for comfort. It optimizes for payoff. For highly mobile coastal foragers, the strip of land along the shoreline is prime real estate. It's where terrestrial game comes to drink. It's where shellfish and seaweed and stranded fish accumulate. Over time, that strip gets crowded by your own group, by neighbouring bands, by rivals who also figured out that the beach is a good place to live. An island, visible offshore, changes the equation. From the mainland, it's unknown but tempting. No human competitors, at least at first. Untapped shellfish beds, fresh hunting grounds, maybe nesting seabirds and naive large animals that haven't yet learned to fear upright apes with pointy sticks. Add in the social factors. Competitive young males eager to prove themselves, kin tensions that make a fresh start attractive, stories about the land under the clouds passed down for generations. The risk starts to look negotiable. Risk management for these people doesn't mean avoiding danger. It means structuring it. They might begin with the narrowest crossings first, from a headland to a nearby islet that stays in clear view the whole time. They experiment in calm seasons, on days when the wind is light and predictable. They send strong swimmers, good navigators, people who have spent their lives reading waves and birds and stars. They learn fast what not to do. Don't leave too late in the day. Don't overload the raft. Don't cross when the wind has been from the south for 3 days straight. The ones who violate these unwritten rules are less likely to come home. Their errors don't propagate. Over generations, this kind of cautious experimentation can extend the radius of safe water. A 2-kilometre hop becomes 5, then 10, then more, especially if there are intermediate waypoints, shoals, small islands, or just known current lines that act like invisible stepping stones. By the time anyone attempts the longest leg toward Crete, they're not ignorant thrill-seekers. They're the inheritors of a long, local tradition of pushing just a little farther offshore, then coming back alive. And yet the physics never entirely cooperate. Currents shift. Storms surprise. Even with knowledge, the margin for error is thin. That tension between danger and opportunity is exactly where many researchers think early seafaring lived. Not as a routine commute, but as a high-stakes, occasionally catastrophic, yet sometimes spectacularly rewarding gamble. So when we imagine archaic hominins facing the gap to Crete, We shouldn't picture a single heroic voyage out of nowhere. We should picture a gradient, small, safe hops near shore, slowly extending into riskier crossings as knowledge accumulates and pressure builds. Which brings us to the crux of the Crete mystery. Could that gradient, by itself, occasionally push a group all the way across by accident? Or do the tools on Crete imply something more deliberate, a decision to aim for that island, not just drift toward it? Let's start with the simplest possibility and work our way up. Maybe nobody meant to go to Crete. In biology and biogeography, there's a whole vocabulary for this. It's called accidental, or passive, dispersal. Animals and plants ending up somewhere new, not because they chose a destination, but because physics dragged them there. You can see it today after big storms. A cyclone rips along a coast. Rivers flood, tear out whole chunks of bank, trees and root mats and soil. All that tangled vegetation washes into the sea. Waves and wind knit it together into rafts, the size of a room, sometimes the size of a house. On those rafts, insects, lizards, rodents, sometimes even larger animals that climbed on in panic when the water rose. Or tsunamis. A big submarine earthquake in the Hellenic Arc can generate walls of water that smash into shorelines, scoop up debris, people, animals, and fling them back out into deep water. If you happen to be on a beach when that crest hits, your decision about travel is suddenly out of your hands. Then there's the quieter version, wind and currents slowly stealing the inattentive. You're out on a log, fishing or playing or trying to cross a little channel. The wind picks up, the current pulls, the headland you were aiming for slides sideways and vanishes. Land behind you shrinks before you realise what's happening. You're kilometres offshore, committed to a journey you never planned. Put all of that together, and the idea that one or two hominins might have drifted out into the Aegean by accident isn't far-fetched at all. It's almost inevitable over tens of thousands of years. The real question is, does that kind of event explain what we see on Crete? To answer that, we need to think like archaeologists, not like scriptwriters. If accidental rafting is the whole story, what should the evidence look like? Picture the purest accident scenario. A storm or tsunami rips a chunk of coast away, with a small group clinging to it. They drift for hours or days and finally slam into the north coast of Crete. Maybe one or two survive the impact and the exposure. Maybe they stagger inland, find fresh water, forage for a while, and then that's it. They die without reproducing. What would that leave in the ground? At best, a tiny ephemeral scatter. A few broken tools where someone napped a flake or two, the remains of a single short-lived camp. No long sequence of occupations, no repeated use of the same locations, no pattern spanning different parts of the island. And even that is optimistic. One unlucky, starving castaway is more likely to drop their tools along a thin, random trail than build recognizable living spaces. Now compare that with a Cretan record. The tools we're talking about aren't all in one weird layer at one freak site. They show up at multiple locations along the southern shore in different terraces and contexts, with signatures that suggest repeated visits or occupations over substantial stretches of time. They're not random oddballs either. They belong to coherent technological traditions. That doesn't prove intention, but it leans away from a one-time shipwreck explanation, and towards something more like people knew how to get here, and they or their descendants kept doing it. To get there, there's another brutal filter we have to pass through: survival after arrival. Even if you grant that accidental rafting can deliver hominins to Crete every now and then, most of those arrivals are evolutionary dead ends unless certain conditions are met. Think of the bottlenecks: water. Unless you land near a spring or a stream, you're in trouble within days. Modern experimenters can bring canteens. Pleistocene drifters couldn't. A group that arrives dehydrated, sunburned, and possibly injured has almost no margin of error. Fire. If you lose your fire in transit, and a storm-tossed log raft is a good place to lose it, you hit that beach without a way to cook, ward off predators, or stay warm in wind and rain. You can, in theory, reinvent fire from scratch with friction techniques, but that assumes you know them and have the right materials. If you don't, your technological level on the island just dropped a notch overnight. Tools. Did anyone cling to a hand axe or a flake as the tsunami tore through? Did a bundle of gear happen to stay wedged in the roots of your makeshift raft? Without stone tools, even skilled hominins are back to pounding, tearing and scratching with bare hands until they can find stone and renap a kit. That's not impossible, but it delays everything. Companions. This may be the most important one. One pregnant woman alone is not a population. 3 adult males, no females, are not a population. You need a mix of ages and sexes, enough people to form a breeding community without collapsing into inbreeding within a few generations. You also need a minimum number of skilled individuals who remember how to hunt, make tools, keep fire going, read a landscape. An accidental event that manages to satisfy all of those constraints at once. A raft that happens to carry multiple healthy adults of both sexes, some portable toolkit, maybe an ember bundle, and then happens to land near drinkable water is already rare. Those people then have to adapt to an unknown ecosystem, avoid lethal mistakes, and raise children who can carry on the traditions that keep them alive. So, if Crete's early hominin presence was purely accidental, you're not just asking for a drift event. You're asking for a drift event that hits a narrow target window of survival prerequisites. And then, because the tools span long periods, you're asking for that miracle to repeat, or to seed a lineage that persists for tens of thousands of years. Could that happen once? Sure. Could it happen again and again, independently, over glacial cycles, always enough to re-establish a foothold after local extinctions? Statistically, it starts to look strained. This is where researchers reach for a principle, sometimes called methodological conservatism, or more colloquially, start with the least extraordinary explanation. At first glance, they drifted there by accident feels less extraordinary than archaic hominins deliberately built rafts and navigated open water to a land they couldn't fully see. Rafts sound modern. Intentional voyaging sounds like something only our species should be doing. But you can't stop at first glance. You have to actually count the improbabilities on each side. On the accidental side, you need rare, severe storms or tsunamis that move people far offshore, the right group composition on the raft, the preservation of some tools and maybe fire, landfall near viable resources, and enough of these events, over enough time, to explain multiple sites and long occupation windows. On the intentional side, you need hominins capable of lashing logs together, enough observational knowledge of currents and winds to know that out there leads to land there, social structures that tolerate, or even encourage, risky exploratory trips, and a tradition that maintains this knowledge over generations. When you lay it out that way, the least extraordinary option may quietly shift. Because we already know hominins tens or hundreds of thousands of years ago were capable of complex tool-making, coordinated group hunting, long-distance land migrations, and, in some regions, possible sea crossings to other islands. We don't have to invent new abilities out of nowhere. We just have to extend skills they clearly already had: planning, cooperation, material engineering from land into water. That doesn't mean accidental voyages never happened. They almost certainly did. Some of the earliest arrivals on island shores in many parts of the world were probably terrified survivors clinging to storm-tossed debris. Those experiences might even have been the spark, the first proof, burned into cultural memory, that the sea could take you somewhere alive, not just drown you. But when we see a pattern like Crete's multiple sites, Similar technological signatures, evidence of repeated presence, most researchers cautiously lean toward a mixed picture. Accidents as the occasional nudge, intention as the engine that turns a one-time disaster into a repeatable strategy. If that's right, then by the time stone tools were being left on Cretan terraces, 130,000 years ago, at least some hominins weren't just passengers on the Mediterranean. They were, in a very early, very precarious way, its navigators. Which raises the next question. Suppose you make it there on purpose, with a small group and a handful of tools. What does life actually look like on this big, empty island? How do you turn a risky crossing into a way of life? Imagine you've just done the impossible. You've crossed the water. However you got there, by accident, by bold experiment, or by a tradition already a few generations old, you're standing on a shore no hominin has ever seen before. What does that world feel like first? It's familiar and wrong at the same time. Pleistocene Crete isn't a tropical postcard. It's a Mediterranean mountain island in an Ice Age world. Sea levels are lower, coastlines stretched farther out, but the interior is still rugged. Ridges and plateaus, steep valleys, seasonal streams that carve their way down to the sea. The climate is cooler than modern Crete, but not Arctic. Winters can be wet, stormy, and raw. Summers can be hot, dry, and unforgiving if you're far from shade and water. Think scrubby woodlands, patches of pine and cypress on higher slopes, evergreen shrubs, and tough grasses on the lower hills. From a survival point of view, the island gives you three basic things: water, food, and stone. Fresh water comes in pulses. Some valleys channel reliable springs that feed little wetlands, even in dry seasons. Others carry flash floods after winter storms and then shrink to muddy pools. Early visitors don't know which is which. They have to walk the drainages, read the plants, taste the soil, listen for frogs and birds that betray hidden water. Food is patchy but diverse. Along the coasts there are shellfish, crabs, maybe stranded fish after storms. Rocky tide pools teem with edible invertebrates if you know how to pry and crush and scrape. A bit inland there are bulbs and roots, wild legumes, acorns from scattered oaks, berries and fruits in season. On slopes and plateaus there are grazing animals picking their way through the scrub. But here's where Crete is strange. Those grazing animals aren't the familiar herds of big antelope, wild cattle, or horses that your ancestors know from the mainland. They're mostly dwarfs. Miniatures. Crete, like many long, isolated islands, evolved its own peculiar fauna. Over hundreds of thousands, even millions of years, big mainland species that somehow made it across, probably as rare rafting events long before hominins showed up, shrank. Evolution turned full-sized deer into dwarf deer, full-sized elephants into pygmy elephants, and then later many of them went extinct. By 130,000 years ago, the Cretan landscape is a palimpsest of that history. Some endemic species are still hanging on. Others have already vanished, leaving only their bones in cave deposits and ancient riverbeds. The key point is that when hominins arrive, they are not walking into a familiar African or Eurasian ecosystem. They're stepping into an island that has been running its own evolutionary experiment, largely untouched by large terrestrial predators. That matters for two reasons. First, it screams long-term isolation. If Crete had been regularly connected to the mainland by land bridges, you'd expect a faunal turnover, big predators and herd animals flooding in during low sea stands, dwarf endemics getting outcompeted or eaten. Instead, you see a classic island pattern. Weird, specialized, often defenseless creatures that have had time to evolve without being culled by lions, hyenas, or packs of hominins. Second, it changes the rules of hunting. A dwarf deer that's never been chased by anything more dangerous than a big raptor behaves differently from a red deer that spent millions of years being harassed by wolves and hominins. It might freeze too long. It might not bolt fast enough. It might use cover badly. For a skilled hunter, that's opportunity. For a clumsy, starving castaway, it's a chance at salvation. But it also means your usual mental maps don't apply. Back on the mainland, your group knows the migration routes, calving grounds, water holes. On Crete, you're starting from zero. You don't know where the dwarf deer sleep, where they lamb, how they move with the seasons. You don't know which cliffs hide vultures' nests or which swamps swallow your feet. So the first years or the first visits are going to look like cautious reconnaissance. Settlement patterns would depend on what brought you there in the first place. If this is true exploration, an offshoot of a mainland group that still has a home base, you might get short visits. Small bands hugging the southern coast, camping on terraces above the sea where fresh water trickles out of the rocks. They'd forage, hunt whatever they can safely target, nap a few tools from local stone to replace what broke in transit, and then leave when resources thin or the season shifts. Those visits would leave delicate footprints, small scatters of tools, a few hearths, butchered bones. Not permanent villages, but marks of repeated curiosity. The same cove might see occupation for a week every few years, generation after generation, as knowledge of that island with good shellfish and strange deer circulates along mainland networks. If instead a group makes Crete their primary refuge, a true colonization, things look different. You'd expect more stable seasonal camps, maybe a lowland winter base near a spring and sheltered bay, with access to fish, shellfish and wood. In warmer months, hunting parties or whole families might move upslope, following the dwarf ungulates into cooler pastures, exploiting nuts and fruits that ripen at higher elevations. Over time, favoured spots, caves with dry floors, rock shelters with good views, terraces out of the wind, get used again and again. Archaeologically, that kind of pattern builds layers, fire residues stacking up in hearths, piles of broken bones, stone chips where tools were regularly repaired, a palimpsest of short visits turning into a signature of long occupation. Fire is absolutely central to all of this. On a new island with no cultural memory to lean on, fire becomes your portable climate, your insurance policy. It dries you after rain, hardens wooden spear points, opens up new foods by roasting, smoking, or boiling them in bark or skin containers. It keeps nocturnal scavengers at bay and lets you stay in one place longer without freezing or getting eaten. Maintaining fire on Crete would shape behaviour hour by hour. Someone has to tend the embers, feed them, protect them from wind. If you lose your fire in a storm and don't know how to make it from scratch, your group might have to trek long distances to find natural sources, lightning strikes, smouldering trees after a burn. That risk encourages cautious, central places, hearths tucked into rock alcoves, fire carried carefully from camp to camp. In the archaeological record, fire leaves clues: reddened earth, ash lenses, stones cracked by heat. But island environments are brutal editors. Coastal terraces erode. Caves collapse. Organic fuel traces vanish. What survives tends to be the most resilient fragments: charcoal in protected sediments, heat-altered stone among napping debris. Tool use and maintenance, too, would quickly adapt to island realities. You can't assume the same high-quality flint or chert you had on the mainland is just lying around. Early visitors would prospect the island, testing river cobbles, scanning cliff faces, learning which outcrops give workable stone. Once they find a good source, that place becomes important. Groups might carry rough cores from the source back to camp and finish the tools there. Or they might set up temporary napping stations right at the quarry and transport finished implements. Either way, the scarcity or abundance of good stone would determine how intensively tools are resharpened, rehafted, recycled. A single large core might be turned into dozens of flakes over its life. Broken hand axes might be reground into scrapers, then into tiny cutting edges. That kind of conservation creates specific archaeological signatures, high ratios of small reworked pieces, lots of retouched scars, clusters of microdebitage where fine resharpening took place. Combine fire and tools with hunting, and you start to see the pattern of daily life. A small group leaves the coastal camp at dawn, spears and hand axes in hand. They move up a valley they've walked before, past a spring they know doesn't dry out even in late summer. They reach a saddle where dwarf deer have been seen. They spread out, using terrain to funnel animals toward an ambush point. A kill, if it comes, isn't just meat for a day, it's bone for tools, hide for wrapping and carrying, sinew for binding, fat for fuel and calories. Back at camp, the carcass is processed with stone edges. Bones are cracked for marrow over the fire. The best long bones are set aside to be shaped, the thickest hides smoked or dried. Each of those steps leaves marks, cut marks on bone, burned surfaces, accumulations of specific skeletal parts as long as later erosion doesn't clean the slate. And that's the final complication. Islands are generous with some clues and ruthless with others. Caves and overhangs can preserve sediments for hundreds of thousands of years, especially if they stay above the highest sea stands. Coastal plains, on the other hand, can be drowned and stripped over and over as sea levels pulse with glacial cycles. A beautiful campsite on a low terrace, 130,000 years ago, might be tens of meters underwater today. So what we see now is a bias sample. We glimpse the places that happen to sit in the right topographic pockets, high enough to escape drowning, sheltered enough to hold on to fragile traces. We find the toughest artifacts, stone tools, thick bones. We infer the rest. From those fragments, Pleistocene Crete begins to resolve not as a blank, empty rock that a few castaways crawled onto and died, but as a potentially workable landscape. A place where small, clever fire, using hominins, could hunt, gather, plan, and return. A place you could integrate into a wider world of movement and memory. And once you accept that picture of people not just arriving, but actually living there in repeatable, patterned ways, you run headlong into the last set of doubts. What if we're over-interpreting the evidence? What if those tools aren't as old as they look or don't mean what we think they mean? Before we crown anyone the first Mediterranean navigators, we need to listen to the skeptics. Let's start by pulling the rug out from under everything we've just been talking about. What if those tools on Crete aren't tools at all? Every time someone claims very old stone tools from a surprising place, the first word that hangs over the discussion is geofacts. Rocks that look like artifacts, but were shaped by nature, by landslides, river tumbling, freezing and thawing, or rock-on-rock impacts during earthquakes. If you walk a cobble beach after a storm, you can find a dozen pieces that have one sharp edge, or a flake scar or two. Our brains are pattern-hungry. We want to see intention in every sharp rock. Archaeologists know this, so when a site like Crete is proposed, the first line of attack is, prove these aren't just weirdly broken stones. How do they do that? They don't rely on one rock, they look at the whole population. Geofacts scatter in every direction, a few sharp here, a few blunt there, every possible angle and shape. True artifacts cluster in a narrow space of form and pattern. You start seeing the same edge angles repeated, the same striking platform types, the same sequence of removals on different pieces, as if someone had a mental template for what a good flake or useful core should look like. Experts test this by doing something deceptively simple, counting. They record the percentage of pieces with clear platforms, the orientation and overlap of flake scars, the ratio of flakes to cores, the presence of bulbs of percussion, those swelling bumps you get when a human hits stone just right with a hammer. They ask questions like, are these edges placed where a right-handed person would naturally hold and use the tool. Do we see standardized shapes emerging out of random raw material? Then they try to break rocks the way nature would. They let machines tumble stones. They hammer them together without aiming. They study talus slopes, river gravels, volcanic debris, and they compare. If the Cretan tools look more like known napped assemblages from Africa or the Levant than they do like any natural fracture population, the artifact case strengthens. If they sit somewhere in the messy middle, skepticism grows. Right now, supporters of the Crete tools argue that the combination of platforms, bulbs, repeated edge forms, and clear reduction sequences crosses the line from coincidence into culture. Critics say the material is crude, weathered, and could still be an unusually napped-looking batch of geofacts. That tension is exactly where science happens. But even if we grant that some of these pieces are real tools, another big doubt appears. Are they really as old as claimed? This is where redeposition and mixing come in. Imagine an ancient river terrace, laid down 130,000 years ago. It gets carved, slumped, and reworked by later floods. Younger sediments slide over older ones, burrows, roots, earthquakes, and sea level changes stir things up. A tool that was once sitting on a surface from 50,000 years ago can get dragged or washed down into an older layer. Or an older piece eroding from a high bank can tumble into a much younger context below. From the point of view of a modern archaeologist slicing through that profile, it can look like a neatly layered cake, older at the bottom, younger at the top. But nature doesn't care about our neat stories. It chews and folds and mixes. That's a nightmare for bold claims. If your stone artifacts come from loose gravels, lag deposits, or heavily reworked surfaces, then the age of the terrace they sit on is not automatically the age of the tools. You have to show that the artifacts are integral to the sediments, not just passengers. People try to test this in a few ways. They look for vertical patterning. Do the tools cluster tightly in a specific horizon, or are they smeared from top to bottom? Are broken pieces of the same tool refitting within a single layer, or scattered across different ones? Do you see undisturbed bedding, fine laminations, delicate features that would have been destroyed if the whole thing had slumped? If the context looks churned, if artifacts float in a mess of reworked material, the safest interpretation is we have old-looking tools in an uncertain age box. Interesting, but not revolutionary. Now add one more complication: terrace correlation. On Crete, as at many coastal sites, the tools aren't sitting under a neat volcanic ash with a known date. They're in fluvial or marine terraces, old shorelines or river plains stepped up along the coast. To date those, geologists often use a mixture of methods: radiometric measurements where possible, but just as often, correlation to global sea level curves. In practice, that can get circular fast. If you assume a given terrace must correspond to a particular high sea stand, say marine isotope stage 5e around 125,000 years ago, you assign it that age. Then tools found on that terrace get called about 130,000 years old. But that original assumption might be off. Uplift rates might vary along the coast. Erosion might have removed certain levels. Local sea level might lag behind global curves. If you're not extremely careful, you can end up with this chain. We think humans were capable of reaching islands by 130,000 years ago. Therefore, we're comfortable tying this terrace to that age. Therefore, the tools show that humans were reaching islands by 130,000 years ago. That's textbook circular reasoning. Skeptics point this out and demand independent clocks, luminescence dating of the actual sediments that bury the tools, radiometric dates from interbedded materials, or at least multiple converging lines of geological evidence that don't all lean on the same single assumption about sea level. So if the current evidence is vulnerable to alternate explanations, geofacts, redeposition, terrace misdating, what would really clinch the case? We'd want the archaeological equivalent of catching someone in the act. First, a stratified site. not just tools sitting on an eroded surface, but artifacts embedded in fine, layered sediments with clear superposition, ideally with microstratigraphy, millimetre-scale laminations that show the layers haven't been jumbled since deposition. Inside those layers, we'd want context, cut marks on animal bones that match the edges of the tools, breakage patterns on bones that scream human butchery, spiral fractures from fresh bone snapping, impact notches where someone struck to open the marrow cavity. We'd want hearths, not just some reddened rocks. Clear lenses of ash, charcoal and burned sediment with sharp boundaries, maybe even multiple episodes stacked on top of each other. If you can date the charcoal with techniques appropriate for that timescale, or at least date the surrounding sediments independently, you start pinning behaviour to a specific moment in time. On the tools themselves, we'd look for microwear and residue. Under high magnification, a flint edge used to cut meat develops different polish and striations than one used to work wood or scrape hides. If multiple tools from the same layer all show consistent usewear, and that usewear lines up with the faunal remains you find nearby, it's very hard to wave that away as random stone breakage. Refitting is another powerful test. If you can take a core and pieces from the surrounding scatter and literally click them back together like a 3D puzzle, showing the sequence of flakes removed, you've demonstrated on-site napping. If those refits stay within a single stratigraphic layer, you've also shown limited post-depositional movement. Find all of that on a securely dated terrace well above any younger sediments, and the conversation changes. Skepticism doesn't vanish. This is paleoarchaeology, it never will, but the burden shifts heavily toward accepting that some hominin, at that time, was really living and working on Crete. Until then, we're in that uncomfortable but productive middle zone. Intriguing signals, plenty of alternative explanations, and no single smoking gun. And that leads to the last question. How does scientific disagreement actually work in a case like this? It's not one team shouting "discovery" and everyone else yelling "hoax" until someone wins. It's slower, more iterative, and frankly more boring from the outside. One group publishes the initial finds and their dating arguments. Others respond with critiques. The assemblage looks too crude, the context is disturbed, the terrace correlation is shaky. Maybe they reanalyze the same stones and classify a smaller fraction as definite artifacts. Maybe they run new dating methods and get a slightly different age range. Then people go back to the field. They dig new exposures of the same terraces. They survey other parts of the island that should, in theory, preserve equivalent levels. They look for caves, sinkholes, and buried basins where sediments might have quietly accumulated for hundreds of thousands of years. They apply better dating techniques as they become available, sometimes overturning their own previous conclusions. With time, patterns emerge. If multiple independent teams keep finding similar toolkits in securely dated contexts on Crete, the case for early seafaring hardens. If instead the original site starts to look like an odd geological fluke, and new work fails to replicate the claim, the conservative position will win out. No solid evidence for hominins on Crete that early. In other words, the story is not fixed. It's being negotiated between rocks, sediments, and skeptical minds, which is why, before we rewrite the history of exploration and navigation, we have to be honest about where we stand now, on an island of tantalizing clues, surrounded by a sea of uncertainty. The next step is to ask what it would mean if the bold interpretation is right, if those clues really do mark some of the earliest crossings of open water in human history. If those clues really do mark early sea crossings, then the story is much bigger than some rocks on an island. It hits the heart of how we think about ancient minds. For a long time, archaeologists drew a sharp line between us and them, modern humans, with symbolic art, long-distance trade, and complex tools on one side. Archaic humans, Neanderthals, Homo heidelbergensis, whoever made the Acheulean hand axes on the other. Clever animals maybe, but not quite capable of the kind of planning and innovation we like to see as uniquely ours. Open water throws a wrench straight into that line. Getting to Crete in the late Pleistocene, even at the lowest sea levels, is not like following a herd across a land bridge you didn't know was there. It's standing on a shoreline, looking at a horizon of unbroken water, and still deciding to go. That decision is heavy. It means someone, or some group, could picture a destination they couldn't see, construct a way to get there, rafts, dugouts, bundles of logs, something that floated and held together, coordinate multiple people to build, launch, and steer it, accept the risk that you might never see land again, and do it anyway. That's not just better stone tools. That's abstract thinking, long-range planning, social coordination, and probably some kind of shared story about why this insane idea is worth attempting. If an archaic hominin did that 130,000 years ago, then the usual timelines we draw in textbooks, symbolic art around 70,000 years ago, modern behaviour around 50,000, stop looking like a clean revolution and start looking like a late flourish on a much older capacity. Sea travel forces us to ask a hard question. Were these primitive humans really so different from us in how they thought? Or have we been underestimating them because most of their greatest risks dissolved into the ocean, leaving almost nothing for us to find? Now stretch that idea outward from Crete to the whole Mediterranean. If at least one island was reachable, others might have been too. Not every coast, not every rock, but enough that the shoreline stops being a hard edge to human movement and starts being a highway with ferry crossings. Imagine archaic groups hugging the coasts of North Africa, the Levant, Anatolia, Greece, Italy. Small movements by land, occasional jumps by water. Even rare crossings, once in a while, can have huge effects over tens of thousands of years. A single successful trip can move. A new way of striking stone, a slightly different core reduction sequence that produces better flakes. Knowledge of a new raw material source. The good chert is 3 days' walk that way, across the water past the inlet with the big cliff. Fire management tricks, plant uses, hunting strategies that evolved in one region, then hopped to another. We tend to think of the Mediterranean as a connected world only once we get cities, ships, and written languages. Phoenicians, Greeks, Romans. But if hominins were already experimenting with sea crossings in the Pleistocene, then a kind of very slow, very fragile information network could have been pulsing around that rim long before anyone carved a trireme. Most of those signals would have been tiny. One group arrives, maybe fails, maybe leaves no descendants, maybe gets absorbed by locals and their ideas die with them. But some ideas stick. A more efficient way of making bifacial tools. A novel hunting tactic for coastal birds or seals. A seasonal migration route that becomes part of a group's identity. Over geological time, even low-frequency crossings can stitch continents into a loose cognitive web. This is why the phrase modern human behaviour can be so misleading. It turns a spectrum into a switch. Before some arbitrary date, call it 50,000 years ago, humans are painted as basically stuck in a simple static way of life. After that, they're suddenly innovators, explorers, artists. Reality looks messier. Neanderthals bury their dead and make glued, hofted tools. Denisovans adapt genetically to high altitudes and maybe develop advanced plant use. Early Homo sapiens experiment with beads, pigments, complex hunting traps. Somewhere in that mix, someone builds a thing that floats and points it at an empty horizon. Are any of those behaviours modern? Depends which checklist you're using. But that's the wrong game. The better question is, what could these people actually do? Could they plan over months rather than hours? Maintain multi-step procedures in their heads? Coordinate labour across families and bands? Imagine future rewards, invisible places, uncertain outcomes, and still act on those imaginings? A sea crossing, even a short one, answers yes to many of those questions at once. You don't need cave art or ivory figurines to show complex minds. You just need a shoreline that didn't stop them. And if the Mediterranean shoreline didn't stop archaic humans, there's no reason to think other coasts did either. Lower sea levels during glacial periods exposed huge swaths of continental shelf. What is now deep water off North Africa, the Levant, the Aegean, the Adriatic, the Sunda and Sahul shelves in Southeast Asia, all of that would have been dry land or shallow, intricate coastlines. Those are exactly the places where early seafarers would have been most active. Narrow straits, island chains, embayments where you can always see the next stepping stone. They're also exactly the places that were flooded when the ice melted. If early hominins used coastal routes to move around Africa, into Eurasia, or down through Southeast Asia toward Australia and New Guinea, most of the physical evidence of that behaviour is now under tens of metres of water. Campsites, butchery locations, launch and landing spots, gone or deeply buried in submarine sediments. That doesn't mean those journeys didn't happen. It means our data set is biased. We're mostly seeing what happened inland, away from the ancient coasts, in the small fraction of environments that preserve stone and bone for hundreds of thousands of years. A believable case for very early seafaring on Crete is like finding one surviving page from a book we thought had never been written. It doesn't tell us the whole story, but it tells us the story existed. Put all of this together, and Crete stops being an odd outlier and starts being part of a much bigger pattern. Humans, and not just modern humans, have a long history of pushing into marginal spaces. High mountains, deep caves, deserts, dense forests, and eventually oceans. Whenever there's a boundary, some lineage of hominins seems to walk up to it, prod it and ask, "What if we cross?" Sometimes that impulse pays off. Sometimes it ends in disaster. Evolution only remembers the successes. The Cretan tools, if they really mark an early sea crossing, tell us that urge to explore, to test hard limits, is not a late arriving quirk of our species. It is baked deep into the hominin story, emerging again and again in different bodies, with different skull shapes and brain sizes, wearing different cultures, but driven by the same restless curiosity. We are not the first to look at a horizon and wonder what lies beyond it. We might just be the first whose ships are big enough, and whose records are durable enough, that some of our journeys won't vanish when the sea rises. But if that's true, then one last question remains. How do we go looking for the rest of those vanished journeys on Crete, around the Mediterranean, and on drowned coasts all over the world? To answer that, we have to follow the shoreline down into the dark. Right now, everything we've talked about in Crete comes from dry land, terrace edges, eroding gullies, road cuts, places where stone tools just happen to be poking out of modern landscapes. But if low sea level coasts were the real highways, then the most important evidence isn't on land anymore. It's offshore. Underwater archaeology is where this story either grows a spine or quietly falls apart. Think about what a real coastal way of life would leave behind over tens of thousands of years. Not just a few stone tools scattered on a hillside, but dense scatters of flakes and cores where people sat and napped day after day. Fire-cracked rock from repeatedly used hearths, bones from seals, fish, seabirds, maybe turtles and coastal deer, shell middens with growth rings that record seasons of use, broken water-worn stones where boats were dragged up or tied off. Almost all of that, if it existed on glacial age shorelines around Crete, is now submerged. So the next phase isn't just another survey on the island. It's pushing archaeology out onto the continental shelf and treating the seafloor as part of the Paleolithic landscape. That sounds impossibly hard, but this is where technology quietly changes the game. We're getting better at seeing under the sea without ever touching the bottom. The first step is mapping, high-resolution bathymetry, essentially super-detailed underwater topographic mapping. Lets researchers reconstruct what the coast looked like when sea levels were 60, 80, 100 meters lower than today. Once you have those paleo shorelines, you can start asking the same questions archaeologists ask on land. Where are the natural harbours, the river mouths, the low protected bays that would have made good campsites? Where are the pinch points, narrow crossings between land masses, island chains that turn a long open water gap into a series of short hops? Using bathymetry, you can trace ancient beaches, drowned dune systems, old lagoon mouths. You're not just staring at a blue smudge on a map anymore, you're rebuilding the actual terrain people would have seen. Then comes remote sensing. Side-scan sonar can pick up texture differences on the seafloor, rocky outcrops versus soft sediment, potential cave mouths, even buried channels. Sub-bottom profilers send sound waves down into the sediment and read the echoes, revealing layered deposits, old soil surfaces, and places where ancient ground sits just below the modern seabed. Put those together with bathymetric maps, and you get targets, specific spots where ancient land surfaces are preserved and reachable. You don't blindly trawl the seafloor, hoping for a miracle. You use predictive modelling. That means taking what we know about where Paleolithic sites cluster on land, near fresh water, near raw materials, on slightly elevated ground above floodplains, and transferring those rules to reconstructed coastlines. If late Middle Pleistocene people liked camping on small promontories overlooking river mouths on land, they probably liked similar spots along the ancient coasts. So you feed those preferences into a model: distance to fresh water, slope, exposure, distance to good stone sources, proximity to likely landing spots. The model spits out high probability zones on the drowned shelf. Then you send the robots. Remotely operated vehicles and autonomous underwater vehicles can run pre-programmed survey grids, flying a few meters above the bottom, snapping thousands of high-resolution images, pinging sonar, even grabbing small core samples. It's slow, painstaking work, but it turns a featureless blue space into a map of possibilities: sand waves here, buried terrace there, an odd angular scatter of stones that doesn't quite look natural. If just one of those targets turns out to be a drowned Paleolithic campsite off Crete, the debate changes overnight. Because now you can do the fine-grained archaeology that's missing from the surface finds. You can systematically sample sediments, date them with multiple methods, look for microscopic charcoal, fish scales, phytoliths from plants, and tiny fragments of bone. You can start to see not just someone was here, but someone was here, repeatedly, using the sea as a main resource. Even on land, new analytical tools can squeeze more information out of those stubbornly ambiguous Cretan stones. Microwear analysis looks at the minute scratches, pits, and polish that form on tool edges when they're used. Cutting soft meat leaves a different wear pattern than scraping a hide, carving wood, boring into bone, or working plant fibers. Under high-powered microscopes, those patterns can be compared to experimental reference collections, where archaeologists have deliberately used replicas on known materials. So a nondescript flake that just looks sharp to the naked eye might reveal under microwear that it spent most of its life slicing reeds or scraping wood. If many tools from a site show wear tied to plant processing, you're looking at a very different behavior set than a handful of butchery flakes. Residue analysis pushes it further. Tiny traces of blood proteins, plant starches, resins, or marine organisms can sometimes survive on stone surfaces, especially if they were quickly buried. If tools from Crete start coming back with consistent residues from marine mammals, shellfish, fish, or specific coastal plants, the case for a maritime-oriented group gets stronger. Meanwhile, raw material sourcing helps reconstruct movement. Every rock has a chemical fingerprint, trace element, and isotopic ratios that vary from one source to another. By analysing that chemistry, you can match a tool found on a hillside in western Crete to a flint seam in eastern Crete, or, in some cases, to an outcrop on the mainland. If most tools are made from local stone, you're looking at small-scale mobility. If a significant portion are made from materials 50, 100, 200 kilometres away, especially across water, you're seeing networks. Throw in more refined dating on stratified terraces, and suddenly those stubborn scatters of stone start to resolve into stories where people ranged, what they did at different spots, whether their patterns changed as climates shifted. But let's be honest about the big missing piece. Right now on Crete, we have tools. We do not have bones. A single hominin tooth from a securely dated context on Crete older than 100,000 years would be world-changing. A partial skull or jaw. It would move this entire debate out of the speculative zone and into the realm where we can say, with some confidence, who actually made those tools. If the fossils turned out to be clearly Neanderthal-like, that would cement them as capable open-water travellers much earlier than most models allow. If they looked more like Homo heidelbergensis or some other earlier form, the implications are even bigger. Complex seafaring pushed back into a period we barely understand. If, in the wildest scenario, the fossils don't quite match any known population, if they belong to some regional lineage that we've only glimpsed in fragmentary remains elsewhere, that opens the door to an entirely new chapter of Mediterranean human evolution. Fossils from nearby islands or submerged caves along the Greek or Libyan coasts could be just as transformative. They'd let us see whether Crete was a one-off experiment or part of a broader pattern of archaic island hopping. But we also have to keep our expectations under control. Underwater archaeology is expensive. Weather is fickle. Sediments can be thick. Stone tools can be hard to distinguish from naturally broken rocks, especially on wave-worked shelves. On land, erosion is both friend and enemy, exposing artifacts, but also moving them. Underwater preservation can be spectacular in some settings, hopeless in others. Progress usually comes as a trickle, a better date here, a clearer stratigraphy there, a small cluster of artifacts in primary position that everyone argues about for the next decade. We should not expect a pristine 130,000-year-old harbour to appear neatly preserved at 80 metres depth with boats still tied up. What we can expect, if researchers keep grinding away at this, is an increasingly detailed, increasingly constrained set of possibilities. The maybe someone washed up here once scenario will get weighed against the people were using these coasts systematically for thousands of years scenario, and data will slowly push us toward one side or the other. And while we wait for that data, there's more to explore if you want to dive deeper into the longer human story behind all this. The full version of that bottleneck episode you heard echoes of earlier, the one about 1,280 survivors, and the 3 human lineages that followed, is collected in book form now. You can find it at sleepytimehistory.com. And there's a discount running this week, if you're curious enough to grab a copy. Back in the field and under the waves, we have to live with a frustrating truth. Some questions might never get a clean courtroom verdict. The sea is a brutal archivist. It erases most of what it touches. Even with better sonar, better models, better microscopes, the story of who first crossed open water to Crete might remain a braided set of probabilities rather than a single sharp answer. But that doesn't make the search less meaningful. Every new survey off a drowned coast, every carefully analysed scrape on a stone from a Cretan terrace, is part of a broader project, trying to see how deep our restlessness goes. Did our urge to push beyond the visible horizon really begin with people who looked exactly like us? Or were there others before us, other humans, other minds who walked down to a shoreline, watched the waves break, and refused to treat that line as the end of their world? To get closer to that answer, we have to keep digging. On the island, in the lab, and increasingly under the sea. So where does all of this leave Crete? When you strip away the headlines and the wishful thinking, you're left with a tight little cluster of facts that are hard to ignore, but not yet strong enough to close the case. On the hard side of the ledger we have stone, dozens, maybe hundreds, of artifacts from multiple localities around the island. They're not random chips that just happen to look sharp. Many show the kind of flaking patterns that archaeologists recognize from other lower and middle Paleolithic sites: prepared cores, deliberate removals, platforms where a napper struck again and again to detach usable flakes. They occur on ancient marine terraces and in old erosional surfaces that, as far as we can tell, formed well over 100,000 years ago, some perhaps in that 130,000-year-old window and even earlier. The dating methods applied to the sediments and the terrace surfaces, optically stimulated luminescence, uranium series on associated materials, geomorphic correlations are all standard tools in the Quaternary toolkit. They're not fringe techniques. The tools themselves look archaic. They're closer in style to Acheulean and Middle Pleistocene industries than to the refined blade and microlith technologies made by later Homo sapiens. That alone hints that if someone stood on Crete with these in their hands, they probably weren't us in the narrow modern sense. We also know that for at least 5 million years, Crete has been an island. No land bridges, no Ice Age causeway suddenly making it walkable. To get there, you have to cross water. Even at the lowest sea levels, you're still looking at tens of kilometres of open sea. Put those facts together, and the core mystery writes itself. Long before modern humans are supposed to have been sailing the Mediterranean, there are stone tools on an island that could only be reached by crossing open water, and the tools look like they were made by pre-sapiens hominins. Everything else, the arguments, the headlines, the skeptical replies, are attempts to explain how that combination came to be. Broadly, there are three main families of explanation. The first is the boldest: intentional crossing. In this scenario, some archaic human group, Neanderthals, Homo heidelbergensis-like populations, or something closely related, developed the ability to move across stretches of open water on purpose. Not necessarily with elegant boats or sails, but with rafts, lashed logs, or simple watercraft robust enough to manage short but real sea voyages. If that's true, then maritime behaviour didn't suddenly appear with modern humans. It emerged as part of a deeper repertoire shared among several lineages. Island hopping, coastal tracking, and maybe even basic navigation weren't a late invention. They were part of the same evolutionary experiment that produced big brains, complex tools, and social networks. The implications are huge. It pushes organised planning, material preparation, and cooperative risk-taking into a time period we usually imagine as dominated by land-bound hunters following herds along rivers and plains. It tells us that thinking like a sailor, reading winds, currents, and coastlines might be almost as old as thinking like a hunter. The second explanation is more cautious. Accidental drift. Here, nobody set out pointing at Crete on the horizon saying, "Let's go there." Instead, a storm, a flood, or a tsunami tore a group of people away from a mainland coast on a mat of vegetation or a shattered shoreline. They drifted for hours or days, terrified, dehydrated, maybe clinging to whatever buoyant wreckage they could grab. Some fraction survived long enough to wash up on Crete's beaches. If a few of them made it ashore with stone tools, and their descendants hung on for a time, they would leave behind exactly what we see: small numbers of artifacts, scattered across the island in places that once would have been near coasts or river mouths. If that's the correct model, it doesn't require sophisticated boat building. It does, however, remind us that evolution doesn't care how a colonization event happened. An accidental founding population can still take root. Rats, lizards, even monkeys have almost certainly colonized islands this way. Humans might have too. The third set of explanations sits in the skeptics' camp: alternative origins. Maybe some of the objects we're calling tools are actually geofacts. Stones fractured by natural processes like landslides, freeze-thaw, or wave action that just happen to look worked. Maybe the dates on some terraces are off, and the surfaces holding tools are younger than they seem. Maybe a subset of the artifacts slid downslope from much more recent occupations and ended up in confusing positions. If those critics are right, then the Crete story shrinks dramatically. Instead of rewriting human maritime history, it becomes a cautionary tale about how easily we can be fooled by broken rocks and complex landscapes. Right now, the data are thin enough that all three families of explanation have to stay on the table. Intentional voyaging, accidental drift, or nothing really happened here beyond natural breakage and mixing. Each comes with different expectations for what further evidence should look like. And that's the key. The way out of this maze isn't better arguing. It's better evidence. Intentional crossing should leave patterns. Repeated landings at similar spots. Layered sites where you can see multiple episodes of occupation separated by clean sediment. Toolkits that show a consistent focus on coastal resources. Maybe specialized gear associated with plant fiber processing, woodworking, or other activities tied to boat building and maintenance. Accidental drift, on the other hand, is more likely to leave a one-off signature. A small number of sites, possibly clustered in just one region of the island. Limited diversity in tool types, maybe no clear evidence of long-term adaptation to marine resources, more like a transplanted inland group trying to make sense of a new environment, then fizzling out. The alternative explanation camp makes its own predictions. If natural processes are doing most of the work, then the supposed tools should grade gradually into obviously unworked stones. Microwear should be ambiguous. Residues should be random or absent. More precise dating of sediments should keep nudging ages forward into the time frame where we already know fully modern humans were around and capable of seafaring. So what, concretely, would settle this? Stratified sites are at the top of the wish list. Not just loose artifacts eroding out of slopes, but clear, undisturbed layers where tools sit on ancient surfaces under younger materials above older ones. Layers that can be dated independently with multiple methods. Profiles where you can point and say, here's a living floor, with tools where people dropped them, in a layer we can confidently place at, say, 180,000 years ago. Fossils would be even better. A tooth, a bit of jaw, a fragment of skull, from a secure context on Crete older than any known Homo sapiens presence. Enough bone to say this is Neanderthal-like, or this looks like Heidelbergensis, or this is something else. Ancient DNA would be miraculous, but even without it, morphology alone could change the whole conversation. Underwater finds might be the real kingmakers. A drowned campsite on an old shoreline, with tools in primary position, hearths, maybe preserved bone and shell, sealed under meters of sediment. A submerged cave with stratified deposits, like the ones that have revolutionized later prehistory in places like Mexico and the Adriatic. Anything that ties human activity directly to those vanished coasts in a way that can be dated and modelled. And on land, more refined dating of terraces and sediments, plus detailed microwear and residue work on bigger samples of tools, will either strengthen or erode the case that these are genuinely ancient, genuinely human-made artifacts. Until those pieces start falling into place, Crete sits in a tantalizing middle zone. Not a solved mystery, not a debunked myth, a signal just above the noise floor of deep time that might be telling us something profound about the humans before us, because that's the deeper question running under all of this. How many stories are missing from the coasts we can't see anymore? For most of the last few million years, sea level has been lower than today. The shorelines where early humans fished, gathered shellfish, carved driftwood, and maybe experimented with floating things, most of those places are gone, drowned under tens of meters of water. Our picture of prehistory is biased inland, toward caves and rock shelters on current land. It's like trying to reconstruct the history of modern cities, but only being allowed to look at mountaintop cabins. Crete might be one of the rare spots where that lost coastal story leaks through the cracks. An island that, by its very existence, forces us to ask, who stood here first, staring back toward a mainland they could no longer see? As new techniques push archaeology further offshore, and as patient field work continues on the island itself, that faint signal may sharpen. It may confirm that archaic humans were bold, deliberate sailors. It may show they were unlucky castaways. Or it may recede, replaced by a more modest, more cautious interpretation. Either way, the search itself teaches us something about who we are. We're a species that looks at an empty horizon and can't help wondering who else, long before us, asked the same questions. If you've stayed with this story all the way to the end, you're probably one of those people. So, if you found this episode thought-provoking, it genuinely helps if you tap like, subscribe to the channel, and share it with someone who'd happily argue about stone tools and sea crossings over coffee. I'd also love to know where you're listening from. Drop a comment with your city, region, or coastline, especially if you're near the Mediterranean or any place where the sea has shaped local history. And if you want to go deeper into the kind of deep time stories we touched on here, the bottleneck, the 3 human lineages, and other prehistoric secrets, I've collected a lot of that into a book. You can read more about it and pick up a copy at sleepytimehistory.com. However this specific mystery turns out, one thing is clear. The edge of the map in human history was never just a line on land. It was a shifting band of beaches, estuaries, and rocky shores that have come and gone with the tides of ice and meltwater. Most of it is gone. But if we keep listening carefully to scattered stones on a Cretan hillside, to faint echoes on a sonar screen, we might recover just enough to glimpse the humans before us. And the first time they decided the sea was not a barrier, but a road.